welcome, or welcome back, I should say, Bob Marley. Much appreciated. Always happy to see you. And yeah, 2 days in a row. I do admit that I have some ground to make up for in terms of the lack of content the past 2 or 3 weeks. So I'm doing my best to make it up. Can't guarantee that I'll make up everything, but I'm gonna give it a good try. And also, thank you so much for the follow. I'm gonna butcher this username. I apologize. Payasito Delandia. Thank you much. Thank you so much for following. Much appreciated. Happy to have you here. I hope you're doing well. And yeah, it was great to be back yesterday. I received a warm welcome. It's always a little bit tricky. I don't know if I can consider myself a content creator at this point, but whatever. However small of a content creator that I am, it's always a little bit tricky if you take a break, and then what happens to your audience if you take a break, or do you have to start from scratch for any sort of extended break? But yeah, it was nice to be back, and nice to receive a warm welcome. And I definitely did not get through all the content that I wanted to get through yesterday, but that's totally fine. I think that's business as usual for my type of streams. I guess better to have too much content, not enough content. I guess is the main message. But yeah, my weekend has been great so far. Pretty relaxed streams, and had a great workout yesterday. Had a great workout today. My bench appears to be actually improving pretty considerably recently, for whatever reason. I'm not questioning. But of course, I can't show it on stream, right? I can't stream my workouts, unfortunately, right now. But yeah, I'm still working on that, and I am very much determined to bring back the workout streams, some form or another. But yeah, I might as well get right into it. So it wasn't so much that nothing really happened in terms of it was mostly just I was too ambitious in terms of organizing, as in I thought I would be able to cover this, and this, and I did get a little bit I wouldn't say sidetracked, because it was great that there was a little bit of an I guess maybe an intermission in the stream, because I had a brief conversation with someone from chat. Yeah. Well, we had a brief Discord call or chat. That was totally impromptu, spur of the moment. Where the Montreal player, they have since kind of taken a step back from Twitch, I think, for pretty much whatever, for the time being, or permanently. Montreal player happened to pass by the stream. They saw what I was talking about, self-acceptance, and they totally want to share their journey about self-acceptance, and kind of certain mental health challenges that they have overcome recently. And Daffy, welcome. Happy to see you. Hope you're doing well. And yeah, I definitely have been absent for the past 2 or 3 weeks, but I'm glad to be back. And we just spoke on Discord for about 15-20 minutes, where he shared, thankfully, that he now recognizes kind of his harsh inner critic, which is definitely related to the self-compassion research that I've shared in the past. He seems to have, from the way he framed it or spoke about it, he has essentially he feels like he has conquered sort of that harsh inner critic, both in the sense that it seems like, this is just what I understand from what he said, that his inner critic is less critical, and also at the same time he seems to be better able to catch himself and prevent him from going down, let's say, a spiral of being overly harsh on yourself. So that was nice to hear, and it was actually at least for me, it was a nice coincidence in that literally as I was covering research about something that I feel is important, someone in chat felt the need and the desire to be hey, this resonates with me, and I want to share sort of my journey that's related to this. I think that's super cool, personally. I don't think everyone enjoyed it, but all I can say is sorry. I more or less follow what I enjoy. I try to listen to the audience as much as I can, but But at the end of the day, if there's something that I enjoy, that I look forward to, and I enjoy talking with people, then I'm just gonna do that. So essentially nothing happened other than I had too much content covered. But we're gonna dive like right into it right from the get-go. But first, starting off with just brief stories, still related to what I covered yesterday. I briefly spoke about the fact that there's this staged walkout in Canada for graduate researchers and postdocs. Basically, researchers, academic researchers. And there now appears to be kind of like whatever a more official story about it, and how this mass walkout that I think is scheduled for tomorrow, or literally less than 24 hours from now, as a result of basically the poor conditions, especially the poor financial conditions. But it's not just financial that are the harsh conditions, but that is a huge part of it. Because as they highlight here, funding for research, academic research, has pretty much like stagnated for decades, as they say here, where it's just been locked, and it's just the expectation that over the past like 20-30 years, each cohort of students has to make do with the public funding that they give you. Even though, I think everyone's virtually aware that the cost of living tends to go up over time, inflation, etc., other factors. And so, you literally are having to make do with less and less. Well, I think our nurses, so definitely, I don't think there's any formal strike. You can just consider the mass exodus of healthcare workers as a strike, as in, if anything, it's worse than a strike. In that nurses here are fed up, and they appear to be like leaving in droves, and there are not enough nurses in training to make up for the loss of not just nurses, but healthcare workers overall. The strikes happened, the complaints happened, decades ago, and those complaints and strikes pretty much like went unheard. And so now it's basically like the tipping point of like, well, okay, if you're not going to listen to us, then, well, there's literally no incentive for us to stay. There's only so much kind of quote-unquote abuse that a person can take. And if they actually can leave and find a new job or other positions, and at some point they're going to do that. And there's totally, and in Canada, there's also a federal workers' strike as well. So there's a lot of strikes occurring, so I don't think it's just Canada, and I definitely come across the UK headlines in terms of strikes. So it seems to be kind of a international thing. So academics are demanding a significant boost to government-sponsored fellowships and scholarships, which haven't changed for decades. Graduate students and postdoctoral researchers at dozens of universities and research institutions across Canada are planning to walk out on May 1st. In protest at government-funded salaries that have remained flat since 2003. Pretty much 20 years exactly. Pay for grad students hasn't increased in 20 years, while there has been 50% inflation over the same period, says Sarah Laframboise, a biochemistry PhD student at the University of Ottawa and executive director of Support Our Science, a student-led campaign group that is organizing the walkout. Scholarships from the federal government provide an annual stipend of $17,500 Canadian for master's degree students, and this typically, depends on the institution. But I can say at the department at my institution that basically you still need to pay tuition, as in tuition isn't waived in my department at my institution, and so you'll need to pay at least roughly $4,000 to $5,000 per year. And so, you'll get this annual stipend of, let's say, $17,500 for master students, but then you definitely have to take away at least $4,000 to pay for tuition. And so you got to make do with 13K over the course of a year as like the bare minimum. Healthcare, yeah, absolutely. Just Day, my city announced that the emergency line had too high demand, so they couldn't respond to pretty much exact same scenarios are playing out here. And even I'll get through this and cover a story related to that, where it's like literally, as a result of kind of like a healthcare crisis in my province, Quebec. Uh, you know, they're opening up clinics where the typical scenario is that emergency rooms are overcrowded because many people understandably use emergency rooms as kind of like their primary care when they need any sort of medical attention because they don't have access to a family doctor. And so, to address the overcrowding of emergency rooms, the government has set up, clinics largely run by nurse practitioners or like well-trained nurses, with the attempt to like ease the burden on the emergency rooms or lessen the burden on the emergency rooms. But you need nurses to open up these nurses' clinics. You need nurse practitioners to be in these clinics. And turns out, we don't have those, or don't have enough of those. Oh, Smash, welcome. Nice to see you. I'm doing pretty well. As I mentioned earlier, I took a little bit of a break from streaming, and also the workout streams are on hiatus for the time being, so that kind of sucks, as the private gym that I stream my workouts from has closed down. But like I said, I'm gonna bring them back somehow. Through sheer force of will, workout streams will return. So, and yeah, so this is for master students, 17,500, which is, definitely not enough. If, let's say, you're an independent student, okay, you want to live on your own, well, that pretty much is not enough, in my opinion. Live on your own and have any sort of, like, decent diet, and any sort of, like, semblance of quality of life. And then it's 23,000 or 35,000 for PhD students, and 45,000 for postdoctoral fellowships. That leaves many researchers in a precarious financial position, says Laframboise. A survey that she and her colleagues conducted of more than 1,000 Canadian graduate students found that almost half of respondents either frequently struggled to make ends meet or forced to make sacrifices to afford necessities. And 30% had considered leaving their studies because of financial hardship. And Smash, I should also ask, like, how are you doing? I hope you're doing well. If I remember correctly, you're managing... Well, I don't want to give anything away. You're managing some healthcare issues, and I hope that you're managing well. The government is losing talent during a labor shortage because they are not investing in research in Canada, says Sammy-Jane Tremblay, president of the Quebec Student Union, who is organizing the walkout at 6 institutions in Montreal. Like, directly related, reason why I know about the walkout, because, like, the graduate student body or association in my department put out the announcement saying, hey, we're walking out. People are leaving research or going to the US or Europe where pay is better. Canada's Science Minister, François-Philippe Champagne, did not respond to a request for comment from Nature's news team. Overdue pay rise. Support Our Science has 3 main demands. First, it wants master's scholarships to increase in value to $25,900, a rise of 48%. Postdoctoral fellowships to increase to $59,200, and the 2 levels of PhD scholarship to be equalized at $35,000. Second, it wants a 50% increase in the number of scholarships funded each year, and a doubling in the number of fellowships. Finally, it wants the size of federal research grants to increase by 50% to allow professors to increase pay for students and postdocs who do not have a federal scholarship. The organization says that these demands are in line with recommendations from the government's own advisory panel on the research support system, which published its report in March. Although only a small proportion of graduate students and postdoctoral researchers in Canada are funded through federal scholarships and fellowships, Laframboise says that Support Our Science made a strategic decision to focus on this funding. Federal scholarship levels are taken as an unofficial benchmark for what students should be paid by the provinces, universities, and other organizations that fund students and postdocs, she adds. Yeah, this is also, something to keep in mind that, so the amounts that they're talking about here, these are specific scholarships coming from the federal government. As in, this is not what every single, assuming the demands are made in that the scholarships are increased to these values, that does not mean that every every graduate student in Canada is actually going to get these, because these are scholarships that you have to apply for, and they are awarded based off of merit, quote unquote. Some amount of merit, but it's basically essentially like merit, which some people will say that's merit. I would say there's other factors also involved. But like, yeah, even if like this is granted, this generally will only apply to technically a minority of students, of graduate students across Canada, because it's only a minority that get awarded these scholarships. Is that something most students will do? I remember when my university announced massive disruption to teaching due to strikes. It ended up being a nothing with like 5 professors with signs outside. So I would say 3 to 4 years ago, or kind of like pre-pandemic, I would predict that the turnout would be quite low. But let's just say, based off of the vibes that I'm getting from, let's say, colleagues, etc., and the Graduate Students Association at my institution, I think there is like kind of an air of like being fed up, of like kind of like can't take it anymore, or like reached a breaking point. And so I think that will affect, and kind of hope that will affect turnout, and that they'll be more motivated, because there's just like more kind of like more recognition that the conditions are not good. I don't know for sure what the turnout will actually be, but I do suspect that it'll be a pretty good turnout. And also another reason why I think that is because recently the graduate student, or one of the student associations at my institution, they have since kind of like changed unions. And like, yeah, there's a whole bunch of like, let's say, whatever, student politics that are taking place. That makes me think that, graduate students appear to be more engaged than ever in terms of like how they're treated, and advocating for better conditions. But we shall see. I'll do my best to report back pretty much after tomorrow. Doing fairly well. My back and neck are perpetually bad. My primary care doctor and the managed care corp that covers all my doctors had to. Ooh, I'm super sorry to hear that. My heart goes out to you. I mean, that's, I guess that is a bright side. I'm glad, definitely. I'm thankful that you're alive. I'm hoping you have some semblance of quality of life. I do remember that you shared, you were supposed to receive some injections at some point. I don't know whether you received them or not, and only share what you're comfortable in sharing. All I'll say is that, like, if you receive them, I hope that they provided some benefit, hopefully long term, but even temporary, kind of like as a bare minimum. So yeah, although only a small proportion of graduate students and postdoctoral researchers in Canada are funded through federal scholarships and fellowships, yeah, like I said, Framboise says that. Oh, I already read this. Yeah, unofficial benchmark. In lieu of any other system to set standards for stipends, universities tend to default to what the federal government provides, set their stipends slightly lower. It says, the hope is that an increase in federal funding will generate momentum for pay rises across the whole system. Supporting students. It is not just students who will be protesting. Mark Johnson is a biologist at the University of Toronto and is helping to organize the walkout there. He has seen firsthand the effect of the flattening in scholarship funding. I was one of the first to get these federal scholarships in 2003, he says, and 20 years later, they are still getting the same amount. Johnson says that this has made it harder to recruit students in recent years. His university has had to set its own stipends higher to deal with the rising cost of living, but many postgraduate students still struggle. Universities also recognize the needs of their postgraduate scholars. Our continued success in attracting top students rests on our ability to provide competitive graduate student financial support, a spokesperson for McGill University in Montreal said in a statement. And McGill in Montreal, often whatever branded the Harvard of Canada. So I think it's personally a little bit overrated. They added that in the, not that it's like a bad institute, but let's just say there's a lot of prestige associated with, I think, like unwarranted. They added that in the 2022-2023 academic year, the university boosted its pool of funding for graduate student support by $7 million, to nearly $28 million to help keep McGill's graduate financial support competitive. Support Our Science has been advocating for higher pay for the past year. Last August, the organization delivered an open letter with almost 7,000 signatures to Prime Minister Justin Trudeau. In interviews last year on CBC Radio and at the Canadian Science Policy Conference in Ottawa in November, Minister Champagne indicated that he supported the request and hinted that the government would soon act on it. But Canada's 2023 federal budget, outlined in March, so, a couple months ago, or basically last month, did not mention any changes to funding levels for research scholarships and fellowships. Walkouts are currently planned at 46 universities and research institutes across the country, and La Framboise expects thousands of people to take part. Ottawa participants will march to Parliament Hill, while in Toronto, they will gather outside the constituency office of Finance Minister Chrystia Freeland. In Montreal, researchers will join a large march by trade unions held each year on May 1st. Together, we will be a bigger force, probably. So, yeah. I'm obviously going to be paying attention. Yes. And, I hope for a good turnout. But yeah, to be determined. So, with that, we'll get into sort of the continuation of where I ended yesterday. So yesterday, I started off with, covering a little bit of research on self-acceptance. I'm basically going to flip the order today, where yesterday I ended with, just giving a little bit of a primer on optogenetics, some basics. So I'm just going to continue with that. And then however far, let's say I get into coverage, and I do plan to cover everything that I plan to cover for optogenetics, I will leave whatever's remaining for covering the more self-acceptance research. And also, I think it's fair to say I cover a decent amount of mental health research on my channel, or a lot of psychology research on my channel. And, starting tomorrow, or I think the entire month of May, is technically Mental Health Awareness Month. So I am probably going to this is not just going to be for the month of May, but probably just, regardless, it's going to be business as usual, as in, I'll still continue to cover, mental health research, psychology research. I might up it a little bit for the month of May, whatever, in honor of Mental Health Awareness Month. But yeah, that's a topic that I'll probably just forward. And what else did I want to say? I can't remember. I had something. It's lost now. I did get the one shot that was for my shoulder upper arm pain, and it worked. I was supposed to get second injection for neck, but lawyer canceled that talk, so... Ooh. Yeah. I'm super sorry to hear that. And I hope you get the treatment you need. And yeah, cost... my positions are pretty clear. I don't think cost should ever be a barrier to treatment. Ever. So, I pretty much covered just this yesterday in regards to optogenetics. Where, in 2010, Nature Methods gave it Method of the Year. And I gave kind of a brief overview of some of the basics, where it's technique at the intersection of, molecular biology, microbiology, neuroscience, and biochemistry. And a lot of things coming together. And as they say here, when I went over this article, a lot of advancements in multiple fields, like the fields that I just mentioned, that allow for this powerful technique that is still being developed. And I'm going to go over, hopefully if I have time, and go over some of the, the more recent research on how this technique is being driven forward in terms of improvements, in terms of optimizations, and what are the ways that they are looking to optimize it. Even though it's a powerful technique, that has, let's say, advanced the field of neuroscience forward by arguably leaps and bounds. There are still, just like with any technique, there are still some major limitations that if these limitations can be overcome, can make the technique even more powerful. So, moved in a little bit too much. Oh, Boy Meets Mini, welcome. Thank you so much for passing by, and shout out to you. Let's see if I can do this properly. should definitely give a follow to Boy Meets Mini for all the CRT, gaming, and racing that they do. And happy Sunday to you. I hope it's going well. Yeah, so associated with this, method of the year article, there was this primer article, which I think is pretty good. It absolutely does. I don't know if it's technically fiber optics, but like, yeah, it's cables, or not cables, but it is, let's say, lights, optical fibers that emit light. I don't know what the technical definition of fiber optics is, but I think it is essentially in that category. As you'll see, like, there are optical fibers that are inserted into the brains of some of the genetically modified mice. Oh, and yeah, what I did want to say, actually, is like I may have encountered a fellow scientist that I might be able to talk about more in-depthly, let's say neuroscience research, and other maybe psychological research, because like they happen to be a neuroscientist, is my understanding, in that they are pursuing their PhD in neuroscience. I'm actually pretty excited about that, if in fact, they want to converse with me about neuroscience research or like other research topics. But if they do, I'm looking forward to that. But I make no promises. It's entirely up to them and their choice. They have the right to refuse. But so far, they appear to be receptive and open to talking about research. I think, yeah, I think it's pretty exciting for me personally. Since, even though I cover psychological research and I cover neuroscience research, I recognize that, it is absolutely not my area of expertise. And in general, I always want to have, actual experts talking about their areas of expertise. I think is the more ideal scenario. And so if like I can actually consult with an expert about some of the neuroscience research or psychological research that I cover, yeah, that is a good thing. I remember learning about how signals can be modulated in fiber, signal processing funds. Absolutely, and I think this technique that I'm going to be going over is pretty much like right in that category of like using light signals through a fiber to basically, kind of like mind control or some semblance of mind to a certain extent, at least in mice and other non-human animals. So in optogenetics, exogenous genes coding for light-sensitive proteins are expressed in cells, and illumination is used to alter cellular behavior. So, I'm gonna do my best to like break it down, because like I understand, terminology that probably not everyone is used to, even though I don't think it's overly complicated. It's a primer article, but still, I want to make it as accessible as possible. But all they're saying here, exogenous genes, just whatever fancy terminology for like outside genes, as in they're taking genes from a certain species or organism, and they're essentially like transplanting them into like different organisms. Like in this exact scenario here with optogenetics, these light-sensitive proteins, as I mentioned yesterday, they come from microorganisms. I think green algae specifically. But the genes for these light-sensitive proteins originating from green algae, they are being expressed in, for example, mice, or certain cells in mice, certain brain cells, such that the particular brain cells or neurons that are expressing these light-sensitive proteins, they should become responsive to a certain wavelength of light once that optical fiber is implanted into their brain. So optogenetics involves the development of light-sensitive proteins, strategies for delivering their genes to specific cells, targeted illumination, and finally, compatible readouts for reporting on changes in cell, tissue, and animal behavior. Right. So, an overall, like, pretty complex thing. where, like I said, multiple fields kind of like coming together. So the first step, light activated proteins, the toolbox. So this is kind of like the foundation of like where it all started. Kind of like the root of it all, because without these light sensitive proteins, you basically couldn't have this technique at all. So optogenetics requires, first of all, light sensitive proteins, which can be naturally occurring or they can be chemically modified to become photosensitive. Yeah, or maybe this is you can engineer them, and protein engineering is a thing. I'll be touching upon that in like the paper that I plan to cover. So tools for modulating the membrane potential. One of the most common uses of optogenetics is for changing the membrane voltage potential of excitable cells, which is kind of like sort of a fancy way of saying, getting electrical impulses, through cells, in kind of like a very elementary way. In neurons, membrane depolarization leads to the activation of transient electrical signals, spiking, which are the basis of neuronal communication. So, you are basically, generating the signals in the neurons, in the brain. Conversely, membrane hyperpolarization leads to the inhibition of these signals. Controlling the switch that operates these currents enables neuroscientists to study how neurons functionally relate to each other and how neuronal circuits control behavior. By exogenously expressing light-activated proteins that change the membrane potential in neurons, light can be used as the on-off switch. So it really is, like, you are pretty much, given the fact that you are introducing these genes or these light-sensitive proteins. Let's say, for example, certain certain cells, the brain of mice. You're pretty much like engineering a switch that, okay, these cells in the mouse brain, they now respond to, that light switch that I can now turn on and off at will. And that's more or less what they're showing here in this figure, right? I'll cover it a little bit more in depthly in a moment. One approach is to use chemically modified so-called cage ligands that become active upon stimulation with light and bind exogenous receptors that were genetically introduced into specific neurons. So this approach here, I think, is the more, well, that's more or less like where it started, kind of like elementary way of how they did this thing. I think it has since evolved to become way more simplified. And let's say streamlined. Ligands can also be tethered to the receptors themselves via a light-sensitive compound that acts as the optical switch. In both of these cases, the light-sensitive soluble or tethered ligand has to be administered to cells or tissues to render them light-sensitive. Yeah, they're using obviously a lot of technical jargon here, but it's pretty much the same message. It's the same overall message of, like, they're trying to get certain population of cells light-sensitive. They're just using a certain strategy to do that. Alternatively, naturally occurring genes encoding light-sensitive proteins such as opsins can be used. These light-sensitive transmembrane proteins are covalently bound to a chromophore. This is just chromophore is just a fancy word for a protein that kind of like has color, so to speak. It's in like the category of like a fluorescent protein, sort of. Retinol, which upon absorption of light isomerizes, for example, this is organic chemistry, activating the protein. Notably, retinol compounds are present in most vertebrate cells in sufficient quantities, thus eliminating the need to administer an exogenous molecule. The first genetically encoded system for optical control in mammalian neurons using opsins was established by exogenous expression of a 3-gene system from Drosophila melanogaster, which is just the typical fruit fly used in research. Neurons expressing these proteins responded to light with waves of depolarization and spiking over many seconds. So, like, yeah, they're just like going over kind of like where the technique started. And like, essentially, it has its like starting point, in fruit flies, generally easily manipulatable. And also, fruit flies, they grow and develop rapidly, so you can have many generations, or you can grow up many generations. Have kind of like a lot of turnover, and also not many people care if you're like mutilating fruit flies. I'm not saying that's a good thing. I'm saying most people are okay with like pretty much like doing whatever to fruit flies. The recent discovery that opsins from microorganisms, which combine the light-sensitive domain with an ion channel or pump in the same protein, can also modulate neuronal signaling, revolutionize the methodology, providing faster control in a single, easily expressed proteins. Like, this is more or less like the more up-to-date approach. That, let's say, resembles more of what's used today. That more or less what I'll be going over in this figure here. I wonder if this can be used to stop tumor cells from growing. It's an excellent question. Instinctually, let's just say, I wouldn't put anything past, let's say, in terms of in the realm of possibilities, as a lot of creative solutions often come from places that you don't expect. But as of right now, I would say currently it's unlikely, but you never know. I can sort of entertain some ideas, like how this technique can be harnessed as like a potential treatment for tumor cells. But I would totally be like speculating, really trying to think outside the box. But you never know. It holds technically some possibility. But I would say at its current stage, unlikely. Be my instinctual. The first of these neuronal switches used channel rhodopsin. So this is like one of those light-sensitive proteins from green algae. When expressed in a neuron and exposed to blue light, this non-selective cation channel immediately depolarizes the neuron and triggers a spike. That's what they're pretty much like going over here. And this is also one thing to keep in mind when it comes to like this technique. Is like, yeah, it's optogenetics and has to do with light, but it's not just all light. There are many wavelengths of light, and they're specifically specifying here blue light, as in like these light-sensitive proteins, and this relates to the paper that I'll be covering in a bit. They respond to a specific wavelengths of light, and they're highlighting them here. As in this channel rhodopsin 2, the CHR2, that stands for channel rhodopsin 2. And you have these variants here. Cheetah, SFO. These are likely all engineered from this main protein. So typically, what's very often done, okay, the best example that I can use is like green fluorescent protein. I'll just like bring that up. So green fluorescent protein, a Nobel Prize was given for the discovery of green fluorescent protein, and also, turns out one of the authors of the paper that I'm going to cover they were one of the Nobel Prize recipients for the discovery of green fluorescent protein. And it comes from, first isolated from the jellyfish, Aquaria victoria. So like, the native protein, the one found in nature, or, as you said, the wild type version, it's a green fluorescent protein. But, since its discovery, okay, we have gone in and done, some engineering, some like protein engineering, and we've pretty much like created all the colors of the rainbow. We pretty much have virtually any color that you want. You have red fluorescent protein, yellow fluorescent protein. You have two. You have M cherry. So pretty much, like from this discovery of green fluorescent protein, you know, biochemists, chemists, molecular biologists, and a whole host of other fields, like they have gone in and engineered, many different variants of green of the fluorescent proteins, resulting in pretty much like all the colors of the rainbow. That's more or less like what you're seeing here. Oopsies, clicked on something. So yeah, and they're sort of highlighting here in this figure. And there's even, so in addition to green fluorescent protein, you also have, and green fluorescent protein is often abbreviated as GFP. And then now you have like EGFP, which is like enhanced green fluorescent protein, which is like, oh, we'll take the original green and we can make it even better, type of thing. That's more or less what they're alluding to here. Some of these will just be like new fluorescent proteins that we've discovered that happen to be different colors. Others will be like actual ones that have been engineered to have that specific color. So that is an excellent question. Of like, what determines the wavelength? And that actually like literally relates to the paper that I'm going to cover. So very often, what will determine the wave? So multiple things will determine the wavelength, and what makes it responsive. And actually, I guess this is maybe a little bit of a teaser, because like that literally is like the topic of the paper that I'm going to cover, where pretty much what they did is they engineered a new channel rhodopsin, a new light-sensitive protein, where they changed its wavelength, or the wavelength that it responds to. Where like before it responded to like red light, this wavelength range, and they got it to pretty much respond to a different wavelength, a presumably better one. And so what determines it is multiple things. Not gonna, it's hard to narrow down to like one specific thing, but it's likely going to be generally either like a molecule that is contained at like the center of the protein, or like the amino acid residue makeup. So it will not be the membrane. It will be kind of like the property of the protein itself. But it's not going to be narrowed down to like one specific thing. Because what they did is in well, I don't want to give it away, but they basically kind of like made a Frankenstein sort of thing, where like they kind of like mixed and matched, where it's like, oh, this flavor, this new flavor of the CHR2, it has like this property, and then this other flavor, also a derivative of CHR2, has like this other property. And so like they basically like mixed and matched to create this like hybrid Frankensteinian new CHR2 that they call Reacher. Okay. And they say, yeah, it's a red shifted. And so it's like, yeah, they're trying to like basically combine all of the best parts of all of the different varieties and put them all together. Oh, and Desolate Mirror, welcome. Thanks so much for passing by. I hope you're doing well. Plants use wavelengths between 400 and 700. Can I get some big grow lights? I mean, you can. I make no promises as to any good outcomes from that. Okay, so like what's special? Like what's so special about these light-sensitive proteins? Yes, absolutely. I'll do my best to shed some light. Is there 1 second? I'm gonna do my, no pun intended. I'm going to do my best to illuminate more on the subject. Let's see. Okay. Okay, so there's these structures here. There is a structure. We're gonna take, this is pretty much like as deep a dive as you can get. We're going to zoom in on the actual protein. Okay. So 6EID. Okay. So, hopefully see that this looks familiar. To that, I can maybe make it better and make it exactly match. I remember. No. I have to do this slightly more difficult way. Do. Okay. Hopefully that sort of matches. Not quite, actually. But whatever. Close enough. Okay. So, the colors actually help. Okay. This. Okay. Yeah. Gotcha. Bear with me. Okay. So this is that CHR2 that they're talking about. So like it's literally this CHR2 in this molecular graphics software. And you can see, okay, it has like, a lot of helical structure to it. And so one of the things that will determine its wavelength, or the wavelength that it responds to, is kind of like, the overall 3D structure that it has, but also at the same time. So, what makes up the helix, okay, that's like the protein part. That is the amino acid sequence. I don't know if you can, I should probably maybe like expand it, make it a little bit more obvious in terms of visualization. So up here, okay, you can see that as I slide, it highlights, pretty much what I'm selecting. These letters up here, that's like the amino acid sequence of the protein. So proteins, or whatever, proteins in nature, in biological organisms, they are typically made up of, 20 different amino acids. Or like, generally speaking, 20 different amino acids. You can kind of think of them, or at least the way I think of them, they are like Lego blocks. Where, you have way more than 20 different Lego blocks. But let's just say when it comes to proteins, you have 20 different Lego blocks to play with. And you can assemble them pretty much in an infinite number of combinations, and, stack them as much as possible, etc., etc. And so each letter here at the top, so like it starts with M, you probably can't make it out. But each letter, that is one amino acid. As in this M here, that should stand for methionine. That Y there should stand for tyrosine, etc., etc. Basically, it's, that one letter is a code for like it stands for this amino acid. And so you have like the entire amino acid sequence here. As I scroll, it selects it, in the graphics. But so in addition to, what makes up a protein, what they call the primary structure of the protein, like you have the amino acid sequence, But when it comes to, like, for some fully folded protein, okay, in nature, they're not just only composed, or part of them, it's not only amino acids. You have other things as well. Typically, very often, you have metal ions. You have things like, magnesium, calcium, etc., etc. And they show some of that here. Where probably if I can properly. Does that even show up? Doesn't look like it. But you have these other things here. At the top. But they're not exactly... There we go. Hard to visualize. So you have these other kind of like... These are not amino acids. They're things kind of like associated or affiliated with the protein, but they are not part of that amino acid sequence. And same thing, you have other things. Kind of like hidden. Show up. Probably not. Oh, there we go. Shows up as like a little squiggly line. Greatest. Yeah, if I can color it something else. Magenta. But like, yeah, you have, so, you have, sort of like buried in there that I colored magenta. You have another thing, okay, that is not an amino acid, okay, and this holds true for many, protein, where there are other things outside of the amino acid sequence that play a part in what it does, and this actually also holds true, in the case of, if I can bring it up. Actually, that's probably the better example. I bring that up. Okay. That's actually kind of, I think, a more perfect example. I'm going to bring up the green fluorescent protein I'm talking about. Okay, there it is. Okay. If I can find it. A lot of stuff. It's probably best I actually... There we go. Well, I've colored it in green. To show in green. Because it's green fluorescent protein. And you can see that it's... So I should have both of them up. Okay. It actually works out a little bit nicely. So on the right here, I have that channel rhodopsin. Okay, that light-sensitive protein. You see it has this very helical nature to it. Okay. But you can see this green, the green fluorescent protein, not helical. Might be difficult to make it out, but it's kind of like has a little bit more of a barrel shaped. And like you have stuff inside the barrel. And so it's like pretty much, it's the overall unique structure of green fluorescent protein that gives it the property that it's green and fluorescent. And there's other things as well associated with green fluorescent protein that allows it to fluoresce green. And then pretty much it's the same principle here too, where it's like, yeah, it's the overall structure, the fairly unique structure of the channel rhodopsin that allows it to be light sensitive. But there are also other things associated with it, like probably some metal ions, but basically some other things outside of the amino acid sequence that allows it to be light sensitive. So yeah, that definitely plays a part in it for sure, 100%. I just want to be aware that's not only that, but that is definitely a part of it, because, like for sure, that's a part of it, because that's literally, that is part of what they do in the paper that I'm going to cover. Is like, yeah, they totally, in making this like Frankenstein new protein, like they are changing the amino acid sequence. And actually, that's literally, oh, I can't, okay. A little bit difficult for me to highlight it. And I can't zoom in totally. But so in this figure here, figure A, which shows their Frankensteinian protein, on the color legend on the right of the figure, you know, you have green, blue, red, yellow, and then a black dot. That black dot, they are literally changing one amino acid. They're pretty much like telling you the modifications that they are making. And they're using different colors because they're pretty much like, they're literally, you know, they're assembling a team, so to speak. In that they took a region from like this particular engineered light sensitive protein, and then they took this other region from this other light sensitive protein, or this other variant of a light sensitive protein, and they're literally like mixing and matching. And then in the case of the black dot, they like literally just like a pinpoint, like one single change. But yeah. So, in addition to like the light sensitivity aspect, that's important. But when we say light sensitive, what are they sensitive to? Or like, what is happening when the light, illuminated? And what allows it to be applicable to neurons, or optogenetics, and kind of like control of like behavior or control of certain regions of the brain, or cells in the brain. And it's my pleasure. I'm hoping it's at least somewhat clear. It's probably not perfectly clear. I'm hoping as we go along, it'll become more and more clear. And I have like a little bit of a short video that seems, I would say, to explain it pretty well, give a good primer also. But yeah, when we say light sensitive, like, what is this special property of the light sensitive? Or what allows it, be adapted for neurons in the brain? Well, when we say light sensitive, or like be special light sensitive proteins, they are special in the sense that when light is of a certain wavelength is, shown on them, they undergo a conformational change. So going back to this, where I'm showing like this is the actual structure here of channel rhodopsin, one of those light sensitive proteins. But you need to be aware that this is a snapshot. Like literally, this is not how they occur in nature. Proteins in nature, just as anything in nature, it's dynamic. It can undergo movement, and very often, at the molecular scale, can undergo like large movements. But basically what we call conformational changes. And that is actually kind of like the special property, or like one of the special properties of the light sensitive proteins, where it's like, when light of a certain wavelength is shown on them, it undergoes a conformational change, and basically it opens up. And that's actually what they're showing here, okay? When they talk about activation. It allows for the passage of certain ions Here they're talking about potassium, or it allows potassium to leave, okay? And then it allows sodium and calcium to come in. So that is actually the real special property that allows it to, be expressed in neurons. Because that is pretty much the overall same process that neurons undergo, send electrical impulses, in the brain. That's actually what occurs in neurons, where you have pretty much ions being flown across or transported across the membrane. But in this case, whatever, uh, it's happening under the presence of light using these light sensitive proteins. That's pretty much what they're showing here. Okay. And also, so you have activation here. So the activation process is, potassium leaves, and then sodium and calcium come in. That's the activation part. And then you have inhibition. And this is another set of proteins. They're still light sensitive. And they go through the slightly different wavelength that they are sensitive to. 589 nanometers. You can see that not quite the same as the activation part. So in this case, okay, when light of this wavelength, is shown on it, it allows for, chlorine to come in. And then this one, in the case of Arch, it allows for protons, or, hydrogen atoms, although we typically call them protons, to exit. So hopefully, it's understandably not intuitive if you're not used to it. But as you can hopefully see, this chloride ion is negatively charged. Okay, and you can see that when light of the 589 nanometers is shown on it, the conformational change that it undergoes, it basically allows for negatively charged chloride ions to come in. And this is across the membrane. What's surrounding these light-sensitive proteins? This is how we depict, a cellular membrane in whatever simplified figure form. So if you, since the chloride ions are negative and it's allowing them to pass through across the membrane, it's allowing pretty much a buildup of negative charge across one side of the membrane. And it's pretty much true as well in the case of the other one, Arch, but it's a slightly different kind of like strategy where you're allowing positive charge to leave, to pretty much like go on the other side of the membrane. But so on the opposite side, you should have more negative charge, or overall more negative charge. That's pretty much like the distinction. Where if you compare it to activation, yes, you allow potassium, which is positively charged, to leave, but also at the same time, you have sodium and calcium allowed to come in. So it's more positive charge on the other end. That's the overall distinction. And that's kind of like what is separating, the activation and inhibition, if I remember correctly. Where it's like, yeah, in activation, you have kind of like the influx of the sodium and calcium, and, the efflux of potassium. But since you have more sodium and calcium, you have like buildup of positive charge across the membrane. As opposed to on the other side in inhibition, in the presence of that certain wavelength of light, you have the negatively charged chloride ions come in, and so you have this buildup of negative charge, as opposed to in the other one, Arch, you're allowing for, positively charged protons or hydrogen atoms to leave. So you're kind of like, in an indirect way, you're building up more negative charge on the other side of the membrane. And they're just expanding it here in terms of like how it functions in an actual neuron. Where like, yeah, you have this channel rhodopsin, and you allow this buildup of positive charge. And then here in the NPHR, you have that negative charge. And so that's pretty much, essentially it allows you to control, with light, neurons. if in fact you can get these light sensitive proteins into neurons. That requires like the genetic engineering. So I'm sure they expand on it. Let's see. So several variants of channel rhodopsin 2 have been developed. Cheetah mutants were engineered as faster channel rhodopsin variants, which can be used to spike neurons at frequencies greater than 40 hertz. The step function opsins, or SFO variants, in contrast, are slower versions of channel rhodopsin 2 that can induce prolonged, stable, excitable states in neurons upon exposure to blue light, and then be reversed upon exposure to green light. Channel rhodopsin 1, or VCHR1, acts similarly to channel rhodopsin 2, but is activated by red-shifted light. So you have this original CHR2, the one that originates from the green algae. And now, as they say, they're engineering ones to kind of like custom build for what they desire in terms of, generating a greater frequency or, whatever property that they're interested in. Oh, absolutely. And you're going to see shortly of like the optical fiber. And like what they actually do, because, you have to think, so the concept is, with these genetically engineered, for example, mice, that they are now in their brain. So think of it in yourself. If you were genetically engineered to have these light sensitive proteins in your brain, they would be in your skull. So they're light sensitive. But then, okay, that doesn't mean that, if you're exposed to that wavelength of light, that, the light sensitive proteins in your brain are going to start doing their thing. Because, like, you have, basically, it's blocked off. You have your skull, a whole bunch of other tissue, that it doesn't penetrate into your brain. And so what they do to overcome that is like they surgically implant, an optical fiber or an LED fiber, whatever, a fiber that emits light into your brain, such that, the light sensitive proteins, or the cells in your brain that are expressing the light sensitive proteins, they actually get the light. They're exposed to the actual light. It's not just like shining a flashlight. And then, it does its thing. It's like literally you have to make sure that the cells that are expressing these light sensitive proteins are actually exposed to the light. And if it's inside your brain, you gotta go to where the cells are, or as close as possible. And that's actually like one of the barriers that they try to overcome through engineering. And that's literally what I'm going to cover in the paper shortly. But like, yeah, it is totally a precise laser, and it requires like surgery, and like it's pretty delicate. Sometimes it is desirable to inhibit neuronal signaling instead of triggering it. Light stimulation of halorhodopsin, that's the NPHR up here. Like, yeah, they're talking about inhibition. Also, so this halorhodopsin also comes from, if I remember, another microorganism, or like the same. Basically, it is found in nature. But it's not like native to mice. It's like, again, just from another microorganism. A chloride pump hyperpolarizes neurons and inhibits spikes in response to yellow light. Recent variants named, so like, yeah, they always give them fancier names. The halorhodopsin, the E usually stands for enhanced, and 2.0, 3.0. So you can see even just like the naming convention. They're trying to like make them better and better. So here's the ENPHR 2.0, and then we have the ENPHR 3.0. Pretty much the same strategy that operating systems use, or whatever the tech world uses. Recent variants exhibit improved membrane targeting in mammalian cells and consequently photocurrents. Light-driven proton pumps, such as Archaeorhodopsin 3, ARCH, MAC, bacteriorhodopsin, and rhodopsin 3, can also be used to hyperpolarize neurons and block signaling. These are all These are those light-driven proton pumps. So yeah, that's when they say proton, they're just talking about this H plus here. That's why I say they usually call it protons. It's a hydrogen atom, but since it's lost one of its electrons, now just a proton. You know, that's what gives its positive charge. Like it's hydrogen atom. Hydrogen is like, number 1 on the periodic table, if I remember correctly. Even though I'm like, 99% certain. Always good to like double check. So you have, hydrogen right here in the top left, number 1. So, it has like 1 proton, 1 electron. And so where was I? For it to have a positive charge, it has to lose an electron. But if it only has 1 electron, then it's now just a proton. So the optogenetic toolbox is quickly expanding as a result of screens that aim to identify new light-sensitive proteins in different ecological niches or by re-engineering existing variants. Like, yeah, since they found these light-sensitive proteins, similar to when they found green fluorescent protein, okay, from that jellyfish, the search was on. This was like a new thing of like, you have green fluorescent protein found in nature in this jellyfish. So maybe we can find other fluorescent proteins of different colors from other whatever organisms. And so, they just search more in nature, or they start engineering them, to get them to where they want to go. And it's the same thing when these channel rhodopsins, or the CHR2, was discovered. Like, this looks like a special, unique protein. Maybe we can find other ones in nature, or maybe we can start engineering whatever variant that we want. And so that's pretty much the strategy. Notably, several of these tools can be used in combination to allow multimodal control of neuronal activity. Recently, CHR2 was used to control the firing of mouse heart cells, extending the use of these tools to non-neuroscience applications. Right. So it's so this is published in 2011. Over 10 years ago. And so the field has advanced since then. But they're even back then, even though it's primarily used in neuroscience or neuroscience research, we are finding more and more uses for it. And they're alluding to that here, where it's like, it might not just be adaptable for, controlling certain cells or neurons in the brain. You might be able to control other cells in the body. So it might be adapted to, heart cells. And I've even come across some research that I'm almost certainly going to show at some point of like, you can also like control, just as you could control, activation and inhibition in neurons in the brain. You should be able to apply the same principles in muscles of like activate the muscle at will, or whatever, deactivate it or inhibit it at will. And there does appear to be some emerging research that when it comes to like studying muscle or muscle activation, that optogenetics can be a tool there. So optogenetic tools have also emerged that allow control of intracellular signaling cascades and molecular interactions. These tools are generally fusions of light-absorbing domains with protein effector domains. Chimeric proteins called optoXRs composed of bovine rhodopsin and the intracellular components of adrenergic G protein coupled receptors allow for optical control of G protein. This is a bunch of not super important. They're just like going kind of like on a tangent, not super critical what you need. That's probably just like too much detail. So yeah, and then they have a second step, delivering the genes. So, like I said, this is kind of like at the interface of multiple fields. So it starts with microbiology, where it's like through microbiology and, looking at green algae, you discover this channel rhodopsin. They talk and they identify the organism that it comes from. I believe this is yeast, if I remember correctly. Or no, it's green algae. Yeah, it's green algae. Phymedomonas, single cell green alga. So it's like, through microbiology and studying, this green algae, they discover that, even though it's just like whatever, a simple green algae has this like really cool protein that we can clearly take advantage of. So it starts with microbiology, and then as they highlight here, like the third step, or second step, delivering the genes. So it's like, these green algae, they're making these light-sensitive proteins, but to make the light-sensitive proteins, it requires that genetic information to make them. And so if you want to, let's say have certain mouse neurons express these light-sensitive proteins, well, then these mice will need the genetic information to express these light-sensitive proteins. And so you need a way to deliver the genes of like, hey, get this mouse have these green algae genes that code for these light-sensitive proteins. So genes coding for these light-sensitive proteins can be delivered to the target cells by transfection, viral transduction, or the creation of transgenic animal lines. So they're basically going through, the different types of genetic manipulation that they can carry out. Expression can be restricted to cells of interest using specific promoters or recombinase-based conditional systems such as the Cree system. Alternatively, the use of viral vectors for gene delivery can allow targeting of specific cells without specific promoters, for example, to target neuronal populations based on their topological connections. So, a lot of jargon here. This is pretty much all to say that, when they want, neurons in the mouse brain to have these light-sensitive proteins, they don't just want all of the neurons in the mouse brain to have these light-sensitive proteins, because that's not overly useful. They are generally targeting, a population of neurons in the brain, saying, hey, let's say we're interested in this region here in the brain. Let's say, for example, I don't know, fear or threat detection. So like the amygdala is typically the brain region responsible for, fear or threat detection or threat sensitivity. And so, if they're interested in, let's say, studying that, then they would want only the light-sensitive protein to be expressed, the amygdala region or the neurons in the amygdala region of, let's say, for example, the mouse brain. And so it's like, it is targeted. And they're going through the different strategies that they use, the genetic strategies that they use, to, target the delivery of the gene. Saying, hey, we only want these specific cells, or like this cluster of cells or neurons, be expressing these light-sensitive proteins. And then the third step, controlled illumination. Precise control of cellular activity via optogenetics depends on the well-defined temporal and spatial control of the illumination light. Wide field illumination can be temporally controlled using an ultra-fast shutter with a constant light source, fast switching of an LED, or one-photon laser scanning microscopy. All cells expressing the light-sensitive proteins in the light path will be stimulated in concert. For in vivo applications, light sources coupled to optical fibers or miniaturized LEDs have been widely used. Alternatively, light patterning approaches can be used to selectively illuminate a subset of cells. One approach uses digital micromirror-based devices to reflect dynamic user-controlled patterns of light onto specific cells or regions of cells. Two-photon scanning microscopy can be used for targeted activation of single channel rhodopsin 2 expressing cells with high temporal control, and recently it was combined with temporal focusing to selectively activate small segments of a cell, an entire cell or group of cells individually or simultaneously. So, again, a lot of jargon and technical terminology. All this to say is like, they don't they don't necessarily always all the time want all of the cells that they have engineered to express these light sensitive proteins. Just as they don't want all of the neurons in the brain to have these light sensitive proteins, even the ones that they have modified have these light sensitive proteins. They don't always want to illuminate them all at once. Neuralicia, welcome. Thanks so much for passing by. And also, let's see if I do this properly. I hope you're doing well. Let's see. But yeah, I'm giving a brief primer, or attempting to give a brief primer on optogenetics. But yeah, so Neuralicia, neuroscience, you should definitely give them a follow. And they're the they're the neuroscientists that I spoke about. They're probably way more qualified to talk about optogenetics than I am, or way more qualified to talk about neuroscience than I am. And also, if I say anything wrong, totally correct me, for sure. But yeah, thank you so much for passing by. Great to see you. I hope you're doing well and enjoying your Sunday. So yeah, reading the outcome. Are you saying you're friends with Karl Diezeroff? Like the Karl Diezeroff? Because I definitely know. Well, I'm not friends with Karl Diezeroff. I obviously know who he is. I think at this point, just about everybody knows who he is. 'Cause I think he's now, his popularity's only increased over time. I'm like, yeah, if you're friends with Karl Diezeroff, then well, it's like, yeah, you are way more of an expert in optogenetics than I am. I know about the proteins. I know about the genetic engineering, but like all the applications, totally pales in comparison than your knowledge. And I'm when you say I'm assuming when you say friends, like you've met them, I guess maybe at a conference, or maybe you visited them. Can't remember at which university, but I think they're in like California. They're at like Stanford or something. Was this like during a seminar, or like those typical whatever seminars where you get to have lunch with the speaker? If so, that's super cool. I'm not gonna lie, also jealous. Although, well, so don't say anything incriminating. But I've only seen Karl Diezeroff in interviews, and he definitely has a specific way about him. And I'm curious how that reflects his actual mannerisms, where he kind of like, I don't know, if I remember correctly, he speaks kind of like pretty monotone, pretty like really chill, and kind of like somewhat of a low voice, arguably pretty soothing. And I'm wondering if that's like his actual like natural way of speaking. 4-step reading the outcome. So the effect induced by illumination of the photosensitive protein needs to be measured in cells, tissue, organisms. Electrodes can be used to monitor the effect of changes in the membrane voltage. Many fluorescence-based biosensors with compatible excitation profiles, some of which are also genetically encoded, can be used to measure different cellular readouts. Finally, behavioral testing can be used to assess the effect of modulating cellular activity in whole animals. So it's like, yeah, in addition to like inducing the signal, they also need to like, measure like the outcome. Or, well, that's pretty much what they're saying here. Reading the outcome. Basically cause and effect. Like they're causing something in the cells or in the organism, and they need to be able to like, read and observe what is occurring. Yeah, that doesn't surprise me. Like, he definitely seems like a genuine person, an authentic person. And if I remember correctly, he's like he's a doctor, a medical doctor, and his formal training is in psychiatry. And I think he still like sees patients, and treats patients, which is like really, he just seems like a super productive person. That it's like, yeah, I can't imagine doing that much work personally, but all the more power to the people that can do that. And I think he's like recently like published a book as well. Yeah. And I think if I remember correctly, like he, yeah, like pretty much the message popped up right as it said book. Like, I think if I remember correctly, like he sets aside time, like write, like specifically. So before we get into, so even though I just gave a primer and text, before we get and dive into this paper, I'm not going to like, I'm going to try to give like what I think are the important highlights of this paper from a biochemistry perspective. Because like, even though this is neuroscience, they are essentially they are doing protein engineering. They're essentially carrying out biochemistry. And this person here, this is the Nobel laureate that I was referring to, that was part of the green fluorescent protein. They have unfortunately since passed away. But like, yeah, they were part of the group, Roger Tsien, that was awarded the Nobel Prize in Chemistry for his discovery and development of the green fluorescent protein. Which is one of the reasons why I cover this paper. Because in addition, so yeah, pretty much what they have learned from green fluorescent protein, since they discovered green fluorescent protein, they were involved in all of the protein engineering, in, you know, engineering all the different variants of now, you know, all the colors of the rainbow of the fluorescent proteins. So they essentially applied many of the same principles of protein engineering when it comes to these channel rhodopsins. It's like, oh, when we discovered green fluorescent protein, we have now engineered a whole bunch of variants. Or we have yellow fluorescent protein, you know, orange fluorescent protein, red, etc., etc. So maybe now, with this channel rhodopsin, maybe we can make an improvements, make it even better, optimize it, etc., etc. Or in this case, get it to respond to a different wavelength of light. And that's why they call it a red-shifted variant. And what, let's say, makes this paper cool, or like, you know, is, let's say, one of the examples of the advancements in optogenetics is like, as you'll see at some point, as we just went through, it requires these light-sensitive proteins that, you know, they respond to light. But then when you're expressing them in, let's say, for example, mice, they very often have to be surgically manipulated to have like that optical fiber inserted in the brain. And so what's cool here is like they're showing an example of like, hey, through protein engineering, you might not need to at some point have to have the optical lights or LEDs inside the brain. You might be able to just like flash a light outside without surgery and have the exact same effect. But hopefully, if my primer wasn't good enough, this short video fills in the blanks or gives the full primer even better.
101. Today, we're going to talk about optogenetics. In neuroscience, various methods have been used to stimulate the brain. For example, with magnetic or electric fields, or with ultrasound. One limitation that all these brain stimulation methods have in common is that they stimulate a specific region that contains different types of neurons, without discriminating between those neurons. Since different neuron types have different functions, wouldn't it be great if we could stimulate a specific set of neurons? Now, this is possible by using optogenetics. The main way in which optogenetics modulates neural activity is through light. It does this through activation of light-sensitive proteins called opsins. Such light-sensitive proteins can be found throughout nature, from archaebacteria to mammals. These photosensitive proteins help these organisms to detect sources of light, which is crucial for their survival. For example, in humans, rhodopsin can be found in the rods of the retina in the eyes, and they convert light into an electrical signal, and thereby they activate the photoreceptor cell. So if there are light-sensitive proteins that can make neurons fire, it may be possible to place these proteins in other types of cells. If we would do this, they also would start to react to light, and we can activate them at will by the flip of a switch. This is exactly what optogenetics intends to do. Okay, so let's say we have a neuron that now has light-sensitive opsins. What happens? In order for a neuron to induce an action potential, in other words a signal from one neuron to another, it allows for the influx of electrically charged particles, such as calcium or sodium. This influx is caused by the opening of so-called ion channels, which happen to be protein molecules. All neurons have ion channels. Some of these ion channels react to a change in membrane potential, and others react to the arrival of a neurotransmitter. But most importantly for optogenetics, some ion channels react to the stimulation of light. The most well-known light-sensitive protein in the field of optogenetics is channel rhodopsin. Channel rhodopsin naturally occurs in green algae and is sensitive to blue light. So that means if you would have a neuron that has channel rhodopsin, you only need to shine blue light on it and it will fire. But the question is, how do we get channel rhodopsin into a specific neuron? That is where we need some genetic engineering. The goal is to change the genetic makeup of a cell, such that it will express channel rhodopsin. Importantly, the morphology and function of different cell types is to a large extent defined by the pattern of genes they express. And which genes they express determines, among other things, which ion channels the neurons have. So if we can change the genetic makeup of a cell, we can make it to have light-gated ion channels. But then the question is, how do we change the genetic expression of a neuron? Well, for that we use viruses. When a virus infects a cell, it enters its own genetic material. Obviously, for optogenetics, we're not just going to use any virus. We are going to make our own that specifically targets certain neurons and that can promote the expression of channel rhodopsin.
And that's also kind of like another field that, like, you require these advancements because, like, so they're in addition to, so in order to genetically engineer whatever the organism that they want to genetically engineer that has these light sensitive proteins, as they're saying here, they're using viruses. And so these are like engineered viruses, so like, multiple engineering feats or, steps have to take place in order to like carry out this technique. And that's what they're referring to here when they talk about like the gene delivery method. I think they mentioned, transfection or viral transduction. That's pretty much just like, one of the many ways that they genetically engineer the organisms or cells that they want to now respond to light sensitive proteins. Yeah, exactly. So that's definitely, I didn't know canine. So I know adenoviruses. I didn't know that they use canine adenoviruses. I'm curious if there's something special about canine adenoviruses.
So in summary, we use artificial viruses to change the genetic makeup of a neuron, such that it now creates light-sensitive ion channels. This will make the neuron fire if light is shined onto it. It is also worth pointing out that there are other light-sensitive ion channels, such as halorhodopsin and archaerhodopsin, which will inhibit the cell if exposed to light. So, optogenetics can become a game changer in treating neurological and psychiatric disorders in the future. However, the translation from research in invertebrates and small mammals to larger mammals, such as primates and humans, proves to be quite difficult. The standard strategies that are used in mice to express opsins cannot be directly applied to primates. Furthermore, the brains of primates and humans are much larger and more complex. And on top of that, there is the ethical question whether such research would be okay to do in humans. Anyway, that's it. We hope you enjoyed the explanation about optogenetics. If you did, consider giving this video a like. And as always, we hope to see you.
That's almost certainly like a better primer, and way more simplified than what I just went through. But like, yeah, light sensitive proteins, get them into whatever organism or group of cells that they're interested in. Multiple ways of doing that. They talk about using viruses to deliver the gene, and then flash some light. So this is just the jargon for kennel cough. To be honest, I think they just use them because, yeah, I don't know for sure, but I imagine that it has to do with like the virulence, or like very often it's just like, hey, this other research group started using them, so we'll just carry on the tradition. At least I know like that's a thing, of like, hey, since this other research group that pioneered it, they worked with them, so we'll just continue using that. So, I attempted to go through all that like foundational work, such that I can do a little bit of a dive on this paper. I'm not going to go through the entire paper because way too technical, and definitely I'm not in the best position to translate all the figures here. Mostly just the ones in regards to like protein engineering and like the overall main messages and highlights. But they're doing something what I would say is pretty cool when it comes to like the biochemistry and protein engineering. And like I mentioned, I literally did a presentation about this paper for a protein engineering course that I took. So, as I just went through in the primer, you have these channel rhodopsins, these light-sensitive proteins, but they are not responsive to the entire, spectrum of light, or the visible spectrum of light. They are responsive to certain wavelengths or range of wavelengths. And it was highlighted here originally in the primer. I think they give for 70 nanometers in the case of that channel rhodopsin 2, and then the ones for inhibition, the halorhodopsins, at 589 nanometers and 575. So, that's cool and all, but that introduces some technical challenges, or maybe some barriers. As high highlighted here, red light is less scattered by tissue and is absorbed less by blood than the blue to green wavelengths that are required by other CHR variants. So, that channel rhodopsin that was like 470 nanometers, that's more towards the blue end, or like the blue, visible spectrum. And I think they explicitly say that in this primer towards the end. Yeah, when express a neuron and exposed to blue light. So one of the problems with that is that, you have a whole bunch of other things in animal tissue that can, let's say, maybe absorb the blue light or like interfere with the blue light. And so like maybe when you're shining that blue light, it might not be getting to like the cells that you've, engineered to express these light sensitive proteins. Or like maybe the signal, the blue light signal might be degraded, by the time it like goes to a whole bunch of like cells, tissues, blood, etc. So what they are attempting to do here in this paper is to see if they can like get it to respond to a different wavelength of light, or as they say here, a red-shifted variant. And the purpose of that, that is highlighted here, that I just went over, is like red light is less scattered by tissue and is absorbed less by blood than the blue to green wavelengths. So like they want, ideally, to use red. It's because it should be able to penetrate deeper into the tissues. And basically, you should be able to deliver the light more effectively or efficiently to the cells that you've engineered. And they're using basically whisker movements as kind of like a proof of concept. And this also this is a proof of concept in the sense that since they were able to produce this redshifted variant, they might have unlocked the potential that you don't need to, surgically implant whatever, an optical electrode or LEDs into the brain. And you could actually just have just a light close to the head of the organism, or the skull of the organism, and just shine the light there, as opposed to directly into the brain. So, I mean, this pretty much gives the background again. I'm still gonna go over it. So channel rhodopsins are light-gated, non-specific cation channels. Cation channels are just whatever, fancy terminology for channels that allow for, positively charged ions to flow through. As highlighted earlier in that channel rhodopsin, it allows for the efflux, or the exit of potassium ions, and the influx of sodium or calcium ions. And that allow the selective depolarization of genetically targeted cells. However, currently available channel rhodopsins are limited by action spectra that typically peak at 450 to 545 nanometers. So the existing channel rhodopsins, they are light sensitive to this range of light, 450 to 545 nanometers. In mammalian systems, such blue-green wavelengths have limited penetration depths into neural tissue. So they're saying yeah, it's great that we have these light-sensitive proteins and that we can deliver them into cells that we want, but they have limited penetration depths into neural tissue, as they are strongly absorbed by endogenous chromophores, such as flavins, hemoglobin, and melanin, and they are scattered more strongly than yellow-red wavelengths. So yeah, they are saying that they have all of these challenges in a mammalian system because you have a whole bunch of basically endogenous chromophores. So this is just fancy terminology for, other molecules that absorb light. And so you have flavins, hemoglobin, that's the iron carrier protein in your blood. And so it's you might be shining light, okay, but a lot of that light will basically just be absorbed by things like this, such as hemoglobin, melanin, and flavins. And so it might not actually reach, the cells or the neurons that you've engineered. So a common means to circumvent this attenuation and achieve deep channel rhodopsin excitation is to insert a thin optical fiber into the target neural tissue. That is their attempt to overcome this challenge. It's hey, we can't just shine a light outside because it'll be absorbed by all of these other things that are contained in the mammalian organism. So we'll overcome that we'll just bring the light as close as possible to the neural tissue that we've engineered. However, this invasive procedure requires precise stereotaxic positioning that may be difficult to perform when channel rhodopsin is expressed in subcortical nuclei, and the fiber may damage neuronal and or vascular structures en route to the target. Yeah, that is my understanding. I'm I definitely take your word for it over mine. Where it's yeah, it requires surgery, and that's also a variable when it comes to you're doing brain research, and so in order to carry out this brain research, you're doing brain surgery, and so to me it's just you're just you're potentially throwing a wrench into your brain research of hey, you sure you've done this fancy genetic manipulation to these neurons, but then you're surgically altering them, and inserting an electrode that you might damage something, as they say. Well, they literally say that, where it's yeah, it may damage neuronal and or vascular structures en route to the target. So it's hey, there's might be some potential for sabotaging your research, maybe. The practical issue of efficient light delivery can be solved by creating a red-shifted channel rhodopsin with spectral peaks near or above 600 nanometers. where light absorption by hemes and scattering cross-sections drop off steeply. Such channel rhodopsins could facilitate the stimulation of deep structures with a light source placed outside the tissue or region of interest, and thus mitigate the need for invasive stimulation. Yeah, I also would imagine, well, again, I always take your word for it, where it's like, yeah, cemented in place, where it's like, yeah, it's an optical fiber, like literally in their brain, and like, I don't know, is like obviously the limits of my neuroscience knowledge, because I'm not a neuroscientist, I don't carry out neuroscience research. But like, I imagine, you know, when you have these mice that have been surgically altered with like that optical fiber in their brain, there's the potential of like, hey, they just like knock it around, and like in the process of them just like going about their day, or like in their cage, they might just like knock the optical fiber around and maybe like damage something. Basically, yeah, I would imagine it has to be cemented in place, because if it's not, like they can just like dislodge it, maybe, or like they can just like literally induce brain damage if they knock it the wrong way. But that is like pure speculation on my part. I have never seen in person a mouse that has like the fiber optics implanted in the brain. I've seen videos, I've seen figures, but I don't actually know like how stable it is or like how deeply rooted. In this study, we engineered a new variant of channel rhodopsin that we named Reacher, or red activatable channel rhodopsin, compared to the previously described channel rhodopsins with red spectral shifts, and C1V1. So like there's a whole bunch of other channel rhodopsins that have been engineered. And like I said, they're kind of like mixing and matching, or like really trying to like, you know, take all the best parts of the different variants and like put them together. And if you take the best from all the other ones and you combine them together, maybe hopefully you get the most optimal one of them all. They are super tiny, so the tissue disruption is pretty minimal, but they can crack. There's a bunch of protocols we do. Yeah, that makes sense. Where it's like, yeah, I imagine it's not, you know, whatever. The cable that I use, or the optical fiber for my internet, like a big thick cable, probably like, I would imagine maybe on the orders of like maybe millimeters or less in terms of thinness. Totally speculating. But I imagine like, yeah, super thin, especially if you're dealing with like a mouse brain. I imagine you don't need a super thick optical fiber for that. But I imagine like, yeah, if they're so thin, they can crack. I would imagine they're pretty delicate. But again, don't actually know. Okay, yeah, microns to yeah, totally makes sense. In this study, oh, I already read that. A more robust spectral response above 600 nanometers, and an enhanced steady-state response to light with wavelengths longer than 600 nanometers. When Reacher was expressed in the mouse Vibrissae motor cortex, we could trigger temporally precise neuronal responses by illumination of the cortical surface with 617 nanometer light through a transcranial window, or evoke Vibrissae movements, just like technical term for whisker movements, through the intact skin and bone at wavelengths ranging from 470 to 655 nanometers. So like, in addition to generating this new channel rhodopsin that responds to a totally different and arguably better wavelength of light, as a result of that, it seems like they're able to like stimulate the cells without the surgery or without implantation of that optical fiber. Expression of Reacher in the facial motor nucleus of the brainstem allowed us to reliably activate Vibrissa motoneurons with wavelengths up to 655 nanometers through the non-invasive placement of a light-emitting diode at the opening of the external auditory canal. So it's like literally like by the ear. Thus, Reacher enables effective and temporally precise, non-invasive stimulation of deep brain structures with channel rhodopsin technology. Yeah, so that is pretty much like the overall main message, or like the main kind of like findings and breakthroughs, or novel breakthroughs of the paper. And let's say the main figure here that, let's say, I'm uh, most uh, most qualified to talk about. They were targeting talking about the brain region, like the motor neuron. Let's see. I literally just read. Yeah, the facial motor nucleus of the brainstem. Which I imagine that's like, well, part of the region of the brain, or their brain, that controls whisker movements, or like whatever. The muscles that respond to whisker movements, or that are in charge of whisker movements. That is pretty much, like, I think, like their proof of concept. Obviously, like nothing too fancy. Just like, hey, with this new variant of channel rhodopsin, and we get some whiskers to move. Gotta set the bar low. And I think there's a diagram here showing. I also think they chose that region of the brain just because I think it's close to the ear, I think. At least based off of what how I'm interpreting this figure here in C. Because like I think one of their intentions is like, hey, can we just have the light source like close to the brain, literally outside of the brain, and then is the light able to penetrate, still reach that brain region? And so I think they just kind of like, hey, this region is like close to the ear. We plan to have the light source close to the ear. And so like, hey, let's just express this new variant in the facial motor nucleus of the mouse. I think. Not 100% certain. But yeah. Yeah, that's what I think as well. And like, let's just say, if you think the same thing, then for sure you're almost certainly on the right track than I am. Or it's like, yeah, I think they're trying to like, this is like, I think, picture perfect conditions. Where it's like, there's clear, I think, as you say, you're pretty skeptical, understandably. And there might be still clear limitations where like, hey, if they wanted to actually like have deep penetration into like, the center of the brain, you probably still couldn't use this protein. Is genetic modification the only method for channel rhodopsins to act in neurons? Based off of my understanding, yes. Because like you are literally not transplanting, but you are getting proteins expressed in organisms that it's not native to them. Like this is literally a protein, and in this case, it's an engineered protein. But at the end of the day, it's a derivative of a protein that is native to green algae, and so you would absolutely need some genetic modification to get them to express it. In addition, also, if I remember correctly, it still requires genetic modification because since this is not a native protein, okay, this is the protein native to green algae or a derivative of it. Very often, if I remember correctly, I could be mistaken, but I believe I am correct. Or like the mice that they use, very often they are genetically manipulated such that parts of their immune system is like suppressed, or like a large portion of their immune system is suppressed. Because if it's not, their immune system is likely to have an immune response and destroy the protein because it's not native to them. In some respects, it's like literally sort of analogous to like organ transplantation, but it's literally almost literally protein transplantation. where since it's not native to them, the immune system will recognize it and destroy it. So I think, and if I remember correctly, very often the mice or whatever organism that they're working with, they have their immune system sort of like down-regulated or suppressed such that they can allow the protein to be expressed. Are the mice head fixed? I'll have to plead ignorance on that. Can't remember. I don't want to give the wrong information. Okay, yeah, so if that is totally wrong, then for sure, correct me on that. I'm totally just trying to go by memory. I might totally be thinking of something else. But I do know at least, well, one of the things that they address here in this paper when it comes to engineering the protein is trafficking, because this is a membrane protein. So it's not just enough to express it or have the neurons like make it. It has to get to the appropriate location. Because going back to this little figure here, the channel rhodopsins, they are embedded in the membrane. So, when proteins are made, they are made not like at the membrane, or they're not made like embedded in the membrane. They have to be trafficked to there. They have to get to the location. And so one of the challenges that they address in this paper is does the protein, or does this new protein, in addition to it responding to this new wavelength of light, does it have better trafficking to the membrane? As in, do you have like more of it in the membrane? I think it used to be that way when they developed things, but not now. Use the viruses. Okay. Yeah, totally. I will fully bite the bullet. That's maybe some of my information, or maybe a lot of my information, might be outdated. And that what happens today, totally not the case. Or I also could have been wrong, even if, as in like flat out wrong, that they didn't have the immune system suppressed. Totally okay with admitting if that was a mistake. But yeah, so the protein engineering side is what is, let's say, I'm most qualified to talk about. And that's literally highlighted here in figure A. If I can highlight it. Highlighting. I don't want all this figure, but either way, it is right here. And it's this figure here. So this is one of the reasons why, like, I definitely prefer to confer with actual experts. Because as much as I like to talk about neuroscience and cover neuroscience research, I at least try to be aware of like the limits of my knowledge. Where it's like, at the end of the day, it's always better to consult with actual experts that like they actually know boots on the ground how it works and all the nitty-gritty details that comes with it. Oh, no worries, Boymates Mini. Always a pleasure. And totally, I appreciate any and all lurks. So yeah, they're doing some protein engineering. And so what they're doing, you have all these variants here. And that's what they're highlighting here in figure 1A, where you have this variant Chef, or Chief. And they're highlighting it in green. Might be a little difficult to see it in the figure, but it's where this N is. That little, sort of basically a green tail. And then sort of like the main body of this Reacher is in blue. So you have this VCHR1. This is like basically kind of like makes up the majority of this new Reacher protein. But then, so it's composed of multiple, you can kind of like think of them as barrels, multiple barrels in the membrane, in blue. But then you have one of them, so you have A to G, but the F portion is coming from a different variant, the VCHR2. And then you have citrine, or YFP, that's yellow fluorescent protein. So that's in yellow here on the cytoplasm side. But yeah, they highlight the extracellular side, so outside the cell. And then you have inside the cell, or like the inner membrane, the cytoplasm. So you have citrine, and then you here, okay, in the black dot, this is basically a point mutation. Where they do L, so it's coded as L171I. So that is the terminology that they use for point mutation. So going back to what I was covering earlier in terms of proteins, amino acid sequence, and that, each of the 20 amino acids that compose proteins, each one has like a 1-letter code. And so they're basically saying like, hey, at position 171, and so they're using this pretty much same convention that's highlighted here. As in, if you go through a protein, each of the amino acid residues is given a number, 1 to whatever, in order, as in, you can even, hopefully you can make it out. Here, at the 1 position, that's an A, that's the amino acid alanine, and then it just goes in order. The second amino acid, that's 2, they're pretty much like counting in order in the sequence of the amino acid. And so this L171I, all they're pretty much saying is like, hey, at this position here, at the 171 position, we changed a leucine to an isoleucine. We basically just switched an amino acid, and specifically switched it from, hey, it used to be leucine, now it should be isoleucine. If I remember my amino acid code properly. I always get some of them mixed up, but I should be isoleucine. Yeah, ILE or I. And then I want to double check. I don't want to misinform. Yeah, L. So that is all they're saying here. Like, hey, we turned an L into an I at the 171 position. Or like 171, that was leucine, and we now changed it to isoleucine. That is a point mutation. And the black dot, they're trying to depict like where in this reacher that point mutation occurred. So if you see in like the C barrel, you have that black dot. So it's like, hey, we're saying right there, he did a little point mutation. And apparently, that appeared to be relevant. Because like it's a fairly large, looks like a fairly large protein. You can see, so if this is the 171 position, and you can see we're at like in like the C barrel, and it goes from A to G. So this is like whatever, 400, 600 amino acid sequence protein, and yet they just like changed 1 amino acid. So the overall description of A, it's like the schematic design of Reacher. Reacher consists of the N-terminus of the chef or chief. So it's like, hey, they just took this one component from this variant of channel rhodopsin, specifically that green. The transmembrane domains A to E and G of VCHR1, transmembrane domain F of VCHR2, and the L171I point mutation. Believe me, no worries. Totally understand. And thank you so much for passing by. And yeah, totally looking forward to the collaboration. I hope you have a lovely evening. I hope you have a lovely Monday, if that's even possible. Have a lovely Monday. I hope that it is. And yeah, looking forward to seeing you again. Examples of C1 view. Oh, I'm going too far. Actually, no, I'm not. So yeah, we'll cover panel B. So panels A and B are the ones that I'm most qualified to talk about. That's pretty much that mostly relates to the protein engineering side. So in addition, to like, this new reacher that responds to a new wavelength, like I said, they need to be able to see or determine that it actually traffics through the membrane. And that's pretty much what they're showing in panel B, where you have reacher here at the bottom panels, and hopefully it's intuitive, but totally okay if it's not. But they're basically trying to show you through, let's say, fluorescence or like, more tiny lights in the cells, that, hey, when it comes to like the reacher panels, you can see more fluorescent stuff. And that they're using that as an indication that reacher is like actually getting to the membrane. Because hopefully you can see that all of like the lights or the fluorescence, it's like, at the membrane. Especially on the panel, the bottom left. I think it's pretty clearly shown, clearly as possible, that, hey, you have reacher pretty much at the membrane, on the outside edges of the neuron, which highly indicates that, hey, not only are the cells making it, okay, they're making this new variant of channel rhodopsin, which they call reacher, it's getting where it needs to go, because you need to have it at the membrane of the neuron. Again, going back to the figure of like the channel rhodopsins, they will only be useful if they actually are at the membrane and they allow for the passage of those ions, either positively or negatively charged ions, pass through the membrane. And so like this is like essentially giving them confidence that, hey, not only are they making it, but it's getting to where we need it to go. And that should be highlighted here in the description of B. So examples of C1V1, so that's another variant, and reacher expression in HEK 293 cells. So this is just like a cell line, as visualized by the fluorescence of fused citrine. So it's this region here. That's pretty much one of the reasons why they included the yellow fluorescent protein, citrine, to be able to like see it, because they don't really want to go on faith that, oh, not only are the cells making it, but we want to know is actually getting where we intend it to get to. So much of the reacher expression was at the plasma membrane, because that's where they want it. They want it at the membrane because it needs to be embedded into the membrane. Whereas C1V1 expression was more intracellular with strong aggregation. And yeah, the scale bar 20 microns. So that's pretty much what they're highlighting. So especially, if you compare the left panels, top and bottom left, in the top left, you have that C1V1, and you can see, pretty dark. I don't see pretty much any illumination or any fluorescence, with the fluorescence coming from that YFP. So that, strongly, at least, I would say pretty strong visual indicator that, hey, in this C1V1, they might be making that variant, but it doesn't appear to be getting to the membrane, because it just appears dark. As opposed to if you compare it to the bottom left, you see, I think, pretty clearly see some fluorescence happening, and the fluorescence appears to be occurring at the membrane, and it appears to be pretty evenly spread out across the membrane. Not perfectly even, but you have pretty good distribution, presumably the reacher. And then if you compare kind of like the top right, or if you just look at the top right, yeah, you see some fluorescence, okay, clearly some bright spots, but they appear to be highly concentrated. And that's what they're referring to when they say aggregation, with strong aggregation, where it's like, hey, yeah, you're getting some of this produced, and like it's getting to the membrane, but it all appears to be like super concentrated at like this region of the membrane, which is much less than ideal, if not like not ideal at all. As opposed to if you compare it to like, the bottom right or the bottom left, you have some nice, generally some nice equally distributed fluorescence occurring, indicating that, hey, Reacher is like nicely evenly distributed across the membrane. It's not just like localized into like certain regions. And then, they test it out, etc., etc. And they go through a whole bunch of tests. This is a pretty big feat in engineering. Because again, there's a lot of challenges that they need to overcome. Where it's like, hey, they might engineer something that responds better to like the wavelength of light that they want, but maybe as they're engineering it in that direction, for whatever reason, and there might be good reasons, that hey, yeah, it responds better to light, but it no longer gets to the membrane. Because again, you're modifying proteins, and when you're modifying proteins, it's very difficult to predict kind of like the infinite outcomes that can occur. And there's always some potential for unintended outcomes. So, the overall main findings. The optimal wavelength range for optical imaging into mammalian tissue is near infrared. Pretty much like the opposite end of blue, which the native channel rhodopsin pretty much exclusively responds to blue light. And so it's like, yeah, it's great that, it's a light sensitive protein, but it happens to respond to light that is like much less ideal for study in mammalian tissue. Like, hey, maybe, and that's pretty much what they're trying to do with this paper. Like, can we take this light sensitive protein and get it more in the red spectrum of light? Where light scattering decreases with increasing wavelength and absorption by endogenous chromophores is reduced, yet absorption by water is still negligible. This paves the way for deeper penetration of light into tissue with reduced attenuation. Optogenetic tools to manipulate neuronal activity should ideally be excited by near-infrared light. Current development of channel rhodopsins has produced many new variants that are maximally activated by blue and green light, such as channel rhodopsin 2, cheetah. Well, they go through all the variants. You have catch, charger, a whole bunch of catchy names. Many of these variants have improved properties regarding kinetics, expression, and amounts of desensitization compared with native channel rhodopsin. However, there has been little progress in the development of red-shifted channel rhodopsin. So it's like, yeah, you have all these different variants that have been maybe engineered or found or both. And, they have all these great, better properties, but still it doesn't address some of the fundamental issues of like, hey, we're still working with light that is not great for working with mammalian tissues. In this study, we engineered two red-shifted channel rhodopsin variants, the Comet and Reacher, that had strong membrane expression in mammalian cells, which is important. Like I said, you need that channel rhodopsin at the membrane. The Reacher variant responded strongly to red light, with a secondary steady-state spectral peak at 630 nanometers, in addition to a primary steady-state spectral peak at 540 nanometers. The mechanism for this shift involves the L171 mutation in the Comet. So, like, that might address the question that you posed earlier, Boy Meets Mini, of like, what is it? Or what is one of the things that allows these proteins to respond to light? At the very least, they're saying here, or they're explicitly saying here, what it is that they changed that allowed it to respond to this new wavelength of light. Because they talk about the mechanism for the shift. So it's like, yeah, the Reacher variant responded strongly to red light, with a secondary steady-state spectral peak at 630 nanometers, in addition to a primary steady-state spectral peak at 540 nanometers. Like, yeah, it responds to basically, 540 or kind of It maximally responds to 540 and 630 nanometers, and they explicitly say the mechanism for this shift involves the mutation of L171 in that V Comet variant. So it's like, is that literally that, 1-point mutation, changing that one amino acid from leucine to isoleucine that appeared to have shifted in the red direction, basically no longer responding to blue light. Past work attributed this position to the redshift of the response spectrum to VCHR1, leucine 126, relative to channel rhodopsin 2, isoleucine 131, which implies that this L171I modification should lead to a blue shift in the response spectrum. However, this idea is based on the charge distribution of all trans retinol in the binding pocket of bacterial rhodopsin in the dark state. And then this is just basically organic chemistry. They're going into like the nitty-gritty details. In bacterial rhodopsin, some transient intermediate photocycle states have absorption spectra, blah, blah, blah. I don't necessarily want to get bogged down in these types of details. Yeah, you can definitely think of it that way. It's kind of like, yeah, it's like, oh, it responds here. Let's say, 540, but if you keep going, it like responds again at 630 nanometers. Actually, flavin absorptions. Okay. Okay. So, yeah, you can definitely, I think that's a fair way to think of it, of like a second harmonic, where it's basically two peaks, or pretty much like almost literally two peaks. And I'll use this as an example. I'm gonna try to leverage my biochemistry knowledge. So yeah, flavin mononucleotide, or FMN. This is part of vitamin B2, or riboflavin. Pretty much why they call it riboflavin, because it contains this flavin mononucleotide, or like this ring structure of flavin mononucleotide. But in addition, okay, it being a component of B2, vitamin B2, it has optical properties, or rather, actually, if you look at a solution of flavin mononucleotide, the solution is typically yellow. And it also basically absorbs light, but it doesn't absorb just any light. It absorbs certain wavelengths of light, just as those light-sensitive proteins that we're covering in the paper. They respond to certain wavelengths of light, or they have now been engineered to respond to new specific wavelengths of light. The same principle holds here, of like this flavin mononucleotide molecule. It also absorbs certain wavelengths of light, specifically two of them. I think it's like 450 and 600, if I remember correctly. Where it's like, so that's pretty much what they're alluding to here. This is called a spectrum. Just as when they talk about responding to light, where they talk about basically absorption spectra, or do spectral peak at 630 and 540 nanometers. When they talk about peak, what do they mean about peak? Well, it's actually peaks that you see in graphs like this, where you have a wavelength on the x-axis, and then here it's absorbance, but it's basically, some sort of like light measurement. In this case, it's absorbance, and you can think of it like pretty much absorbs light at this wavelength. So when it comes to that flavin mononucleotide, they highlighted 450 here because this flavin mononucleotide, it happens to absorb light maximally at that wavelength 450 nanometers. But it also has two of them. You can see that there's two peaks. So it has like a rise, peak number 1, a valley or a dip, and then it goes to 450. You can kind of think of it pretty much same thing as the 630 and 540 nanometers, where it's like, yeah, you have peak number 1 at like 540, and then probably almost certainly a dip, and then a second peak at 630, where it's like, hey, these light-sensitive proteins, their new peaks are now at 540 and 630 nanometer. And I think this first peak of flavin is like 380. Nope, never mind. I don't want to get too bogged down. Yeah, 353. I'm just like satisfying my own curiosity, sure that I remember my basic biochemistry correctly. Let's see. So yeah, wrapping up, and then so yeah, I'm gonna show you. I mean, I showed this toward the end of yesterday's stream of like, hey, their proof of principle was whisker movements, and they actually showed. So they have a little diagram here in C, figure 6C. I've highlighted here. So you have their mouse, okay, and you have the wavelengths here, okay, and you have their light source, and you have the I think the facial motor nucleus or something like that, or the the facial motor nucleus, yeah. So FN. So like the light source, instead of like the optical fiber, like literally being surgically implanted into the brain, they have it just like close to the ear. And so the schematic of an awake mouse expressing Reacher in the facial motor nucleus, photo activated by LEDs placed at the opening of the external auditory canal. Basically fancy terminology for at the ear. Vibrissae movements, or whisker movements, were recorded with high-speed video. So essentially what they did is, they have their light source at the ear of the mouse, and, the facial motor nucleus region in the brain appears to be close to the ear, so it's expressing the Reacher. And so, like, basically the neurons in the facial motor nucleus that are responsible for whisker movements, they should be expressing Reacher. That is now this new light-sensitive protein that responds to these new wavelengths of light. So when they put the light source close to the ear, and they shine the light at this specific new wavelengths, you should be activating those modified neurons in the facial motor nucleus that should be in principle moving the whiskers of the mouse, and that's actually like what they demonstrate. There is some video associated with this paper that they show it like, hey, with a pulse of light, the whiskers move. And that's pretty much, so they have it here in picture form, where it's like, in figure E, or 6E, so it's this panel here, we have, oopsies. Stop it. Stop highlighting. Oh, I think this is naturally highlighted. I'm just an idiot. So yeah, no light and with light. And so with no light, you have the whiskers in these position, and then with the light, the whiskers appear to move in a new position. So they have it, whatever, snapshots, but they appear to have actual video that I'll show in a moment, where it's like, yeah, with each pulse of light, the whiskers move. So was last two paragraphs, then I'll go to the video, or last couple of paragraphs. Although Reacher has an improved spectral response to light at wavelengths greater than 600 nanometers, it still suffers slow kinetics in its channel closure rate compared to variants such as channel rhodopsin 2, so the native one, Chief, channel rhodopsin D, and Cheetah. So it's like, yeah, even though it has this new and better property, there appears to be a little bit of a drawback. That basically doesn't appear to be as responsive or quickly responsive. In the blue light activated channel rhodopsin variants, single point mutations that improve the channel kinetics also reduce the channel's light sensitivity. The other known channel rhodopsin mutation that increase the channel kinetics, so it's like, yeah, a whole bunch of mutations here and new variants, does so at the expense of reduced light sensitivity and reduced photocurrents. In the context of Reacher, or new fancy protein, this E to T mutation increases the channel kinetics and surpasses C1V1 in terms of kinetics, but blue shifts the spectral peak to 550 nanometers and increases the desensitization of the channel. We did not find incorporation of this mutation useful in the current development of Reacher. Important future goals in developing red-shifted channel rhodopsin should include improving light sensitivities and faster kinetics simultaneously, and reducing the activation of these variants by light below 500 nanometers to allow for the independent manipulation of two populations of neurons with two different wavelengths of light. So yeah, probably it probably doesn't impact it too heavily, but there likely is. So basically, it should not significantly impact the function, but it likely has some sort of mild impact. But it's almost certainly not significant because the cells seem to just operate just fine, and still like go about their basic functions. But it totally is a concern, actually. It is totally something to be mindful of, where probably going back where they show the fluorescence and how it gets to the membrane. Where was it? Lots of scrolling. Yeah, here in panel B. So it's like, yeah, when you look at like the bottom panels, I wish I could zoom in more, but I can't. This maximal zoom. This reference map. But like, yeah, if you compare the bottom panels with Reacher, you have it generally nicely evenly spread out in the membrane. But as they say there, when I read the description, if you look at the top panels, or specifically the top right, where it's like, yeah, you're getting the Reacher, and it's getting to the membrane, but it's super highly concentrated, or like highly localized at like very small regions, and not spread out throughout the membrane. In that particular circumstances, there is a much greater concern that it actually impacts the function of the cell. Because generally speaking, as they say here in the description of the figure, that like you have strong aggregation. Generally speaking, so Reacher is a protein. Like I said, light-sensitive protein. This brand new engineered light-sensitive protein. And generally speaking, if not almost universally speaking, protein aggregation virtually never a good thing. I mean, this is like one of the mechanisms of, let's say, Alzheimer's, and a whole host of, let's say, protein aggregation conditions, where it's like, yeah, generally speaking, as a rule of thumb, like in an organism, protein aggregation, not a good thing. Where it's like, yeah. Where it's like, yeah, protein aggregation and neurodegenerative diseases. And so yeah, Alzheimer's disease, Parkinson's disease, Huntington's disease, and ALS, or amyotrophic lateral sclerosis, where where it's like these are generally speaking protein aggregation conditions, or like something is happening at the protein level that like that we don't really fully understand why, but things are starting to aggregate. And that's one of the reasons why, like I say, protein aggregation virtually never. So it's like, in that case, specifically when looking at the top right panel, if you are having that much aggregation, or when they specifically say strong aggregation, there's a much greater concern that it is, if not much greater likelihood, that it is disrupting the function of the cells in that case. So that is totally, that is an excellent question to ask, because that is definitely something to be mindful of. Especially when you are engineering, you're engineering proteins, that you're technically engineering cells, because these new proteins are being expressed in cells. So you definitely, when you're modifying cells, especially in an organism, you always have to keep in mind of like, hey, how is this modification going to affect the functioning of the cell? So we were able to exploit the spectral advantages of Reacher to achieve efficient activation of expressing neurons through fur, skin, and intact bone of adult mice with red-orange, red, and even far red light. That's pretty much one of the main kind of like novel things, or like great things about this paper. As like I said, they are carrying out optogenetics without the surgical implantation of the light source or optical fibers in the brain. This enables new in vivo applications of transcranial and deep brain stimulation with optogenetics. Transcranial stimulation is essential for many chronic studies, as cranial windows can lead to activated microglia and astrocytes as part of an inflammatory response that in turn alters neuronal physiology and plasticity, as well as heel vasculature. And if I remember correctly, I could be mistaken, but if I remember correctly, microglia and astrocytes, they're essentially kind of like the immune system of the brain, or like the immune cells of the brain, if I remember correctly. Alternatives to our approach for non-invasive transcranial stimulation include clinically approved treatments for severe neurological disorders and stroke, such as electroconvulsive therapy, repetitive transcranial magnetic stimulation, and transcranial direct current stimulation. These techniques do not, however, have the spatial and cellular specificity that can be achieved through optogenetics. Thus, optogenetic approaches using redshifted anorhodopsins such as Reacher have the potential to improve the efficiency of transcranial stimulation to treat neurological disorders. Right, so they're kind of like talking about a potential therapeutic application, which I would say pretty ambitious, since, like, you know, they've definitely shown something very cool. They've shown something very cool, like in mice, and you know, they're talking about, you know, like this has potential therapeutic applications when it comes to, you know, human conditions, or diseases, which, you know, that's a common theme when it comes to whatever, any life science paper. Hey, how does it apply to us? And where's the advantage for humans? So, but they're saying this with like some justification, because, you know, there's a lot of methods, okay, when it comes to treating neurological conditions that require kind of like access to the brain or stimulating certain regions of the brain, and doing that in humans, you know, not an easy thing. Very often requires like surgical intervention, where it's like, I mean, literally, one of the therapies, the more invasive, or not extreme, but kind of like last resort therapies, I think for depression, if I remember correctly, is deep brain stimulation, where it's like pretty much in the terminology, it's deep brain stimulation, stimulating deeply, you know, a certain region of the brain. But that, if I remember correctly, that typically requires like, surgical implantation of a device, in the region of the brain that will like deeply stimulate it. I want to fact check that because I don't want to spread incorrect information. Yes. So yeah, deep brain stimulation in the treatment of depression. Which is like, yeah, it's totally like a thing. And I think it's very often used as like a last ditch effort because I think it is pretty invasive. I think it requires, I'm pretty sure. Yeah. Given that deep brain stimulation involves neurosurgery in patients with severe psychiatric impairment, ethical questions, blah blah. So like, yeah. Totally, my information might be outdated. Totally correct me if I'm wrong. Fair point. I have no doubt that, there are likely advances. But I think, the traditional approach may be outdated. This is 2014. Yeah, fair. But that's basically what they're alluding to when they wrap up here in the closing paragraphs in the discussion. It's like, hey, we've shown that, in the mouse that, you can stimulate the region of the brain that moves the whiskers, right? So it's like, hey, super ambitious. We just, have light close to the ear and stimulated the facial motor nucleus of the mouse. And we showed that it works as the whiskers move. So like, hey, maybe, okay, when it comes to humans, and maybe in applications that require, deep brain stimulation, maybe you don't need to do the neurosurgery. Maybe you can just, get them to express the light-sensitive protein and, have the light source outside. Obviously, that's very ambitious, and there's a lot of technical challenges that would need to be overcome. Numerous technical challenges. I'm not an expert, but even I can foresee just like, an infinite number of technical challenges to overcome to get to that point. But they're not wrong in terms of, like, in principle, it could hypothetically work. It's just like, that very ambitious future projecting. But it would totally be super cool if it actually happens. Yeah, I'm definitely not the most up to date when it comes to brain embedded devices, as you say, or brain implantation. But I think generally speaking, when it comes to, let's say, treating brain conditions, I don't think we're quite there. Or at least treating brain conditions with a strategy of stimulating a region of the brain. I think, as far as I can tell, still the mainstay is like, hey, brain, let's do neurosurgery and, put the device, in the brain or close to the region in the brain. Yeah, I would assume so. I'm gonna have to update my knowledge, and then I'm probably gonna have to do a stream devoted to new brain implantation devices. Or like, how do we do deep brain stimulation now? Because I have no doubt that my knowledge is outdated. Where it's like, the way I learned about deep brain stimulation and covered it, it's like literally it's neurosurgery, and like you put the device that's doing the stimulating inside the brain. So even though, I'm a scientist, and I love learning about new technologies, I am kind of like, whenever those brain implants come, I'm not going to be one of the first ones to sign up. I will totally be holding out probably for quite a while. In the present study, we introduced the channelrhodopsin reacher through injections of an engineered virus directly into the region of interest, which is like, multiple feats of engineering. So they've engineered the virus, and then, you know, the virus, is basically delivering our genetic engineering. So it's like we're using engineering to carry out engineering. Engineeringception, so to speak. Like I said, with this technique, you know, you have multiple intersections, or an intersection of multiple fields. You know, they're talking about protein engineering, and that's what gravitates towards me, or what I gravitate towards too. And you know, you have genetic engineering, you have whatever, yeah, whatever, the actual neuroscience, etc., etc. Let's see. In future work, it may be possible to label specific populations of neurons by retrograde transport of reacher from a known target. For example, pools of motor neurons in the brainstem or the spinal could be labeled by injection into specific muscles rather than into motor nuclei themselves. Such an approach would substantially reduce the invasiveness of an optogenetic strategy for future therapeutic use. Further, one could label opposing muscle groups with short or long wavelength anorhodopsins to permit differential optical control of opposing muscle groups. The weak absorption of short wavelengths by reacher will not compromise this strategy if the anatomically deeper motor pools are labeled with reacher. Reacher may also facilitate neurological treatment and neuroprosthetic control through transcranial and possibly transvertebral stimulation. So it's like, yeah, again, they're pretty much like closing off like, hey, there might be some therapeutic applications when it comes to treating neurological conditions, and, you know, transvertebral stimulation, which again I think is pretty ambitious, but I totally understand why they're saying. And so to close off this paper, you know, show the video, that the supplementary video that's associated with it. Edit. Do. So, you know, it's not the most exciting video. All you need to know is, like, this is one of their, you know, modified mice. Or specifically mice that has the facial motor nucleus that is expressing their new reacher. Okay, and now they're testing it out of like, hey, does it actually respond to light? And the way that they're testing out to determine whether it responds to light, it's like, yeah, it's in the facial motor nucleus that is responsible for whisker movements. And so they're using whisker movements as the proxy. If in fact the whiskers, the movement of the whiskers, corresponds to the pulse of light. And at the bottom there, with the red vertical bar, that is their pretty much at each of the red vertical bars, that is where they are shining the light. That is the, you know, that's the red shifted variant. That's why they're using red, as it's in the title of the paper. It's a red shifted variant. So each time that they shine the red light, the whiskers should move. Not overly exciting, but that's pretty much it. Each pulse of red light, the whiskers move. And here, like the red light, you know, it's off camera, but it, you know, it's like I said, it's not through implantation through an optical fiber in the brain. It should be just like by the ear, just like pulsing the red light. You know, they might be fabricating, you know, some data because they're not showing the light source. But I trust them that, you know, it's actually just a light source that's close to the ear. Well, that's pretty much it. At least, you know, what I wanted to cover about this paper. But, and this paper is fairly old. I think it's like 9-10 years old. Yeah, October 2013. So like almost a decade old. But This is a more recent paper, I think 2018, 2019, yeah, 2019. Where, you know, they're still trying to make these channel rhodopsins better. And now, we're, you know, leveraging, whatever, machine learning or algorithms, and pretty much towards, like, the same end goal. Arguably, here in this reacher, you know, they're trying, or they're making an attempt to engineer a channel rhodopsin or a light-sensitive protein that allows for minimally invasive excitation or stimulation. And that's pretty much the same principle here, where machine learning guided channel rhodopsin engineering enables minimally invasive optogenetics. So, and you know, this is pretty much, this was carried out by, you know, pretty much protein engineers, or, you know, biological engineers, where if you look at the authors, they're affiliated with a division of biology and biological engineering, California Institute of Technology. You have the division of chemistry and chemical engineering. And then, well, I think that's pretty much it looks like. But pretty much, you know, biology and chemistry or chemical engineering. And here in this one, you know, pretty large collaboration. And like I said, this Roger Tsien researcher, you know, pretty big researcher, because like I said, was the part of the group that won the Nobel Prize for the discovery of green fluorescent protein, which has since essentially revolutionized molecular biology, and even also neuroscience as well, because like these fluorescent proteins also are used to map multiple uses, but one of them is like to map out the brain, resulting in pretty pictures like this brainbow, where it's like you have all of the fluorescent proteins being expressed in neurons in the brain. I think this is the hippocampus, to be specific. And this is pretty much like one way to basically attempt to visualize kind of like the connectivity in certain regions of the brain, or just like how connected it is, or like how it's wired, and where do all like the neurons go. Because like it's very difficult, or exceptionally difficult to map out the brain. It's a little bit of a tangent. But yeah, all that to say, it's like they are still trying to engineer, at least, you know, as recent as 2019. I think it still holds true today. But I did not search, let's say a 2023 paper. But I'm pretty sure it's still occurring. Where it's like, yeah, we engineered light-gated channel rhodopsins whose current strength and light sensitivity enable minimally invasive neuronal circuit interrogation. Current channel rhodopsin tools applied to the mammalian brain require intracranial surgery for transgene delivery and implantation of fiber optic cables to produce light-dependent activation of a small volume of tissue. So yeah, still the same challenge that they're talking about, that was spoken about here, this paper, in 2019, or rather 2013, where it's like, hey, optogenetics, great, super cool, big step forward, huge giant leap when it comes to neuroscience research, but still some technical challenges that we still want to overcome. And they're still talking about how invasive it is, and, you know, surgical implantation. So to facilitate expansive optogenetics without the need for invasive implants, our engineering approach leverages the substantial literature of channel rhodopsin variants to train statistical models for the design of high-performance channel rhodopsins. With Gaussian process models trained on a limited experimental set of 102 functionally characterized channel rhodopsins, we designed high photocurrent channel rhodopsins with high light sensitivity. 3 of these, chargers 1 to 3, enable optogenetic activation of the nervous system via systemic transgene delivery. Charger 2 enables light-induced neuronal excitation without fiber optic implantation. That is, this option enables transcranial optogenetics. Have not dissected this paper yet. I'm probably going to at some point. But like, yeah. Still trying to deal with the same technical challenge and make optogenetics better. This is how I think this is a good example of how science works. Of like, this technique, optogenetics, like I said many times before, I'm repeating myself. But it's through discoveries in microbiology, discovering these light-sensitive proteins, through discoveries or innovations in genetic engineering and manipulation. It allows for this technique of optogenetics in neuroscience, and it's expanding into other fields. And yet, despite the huge innovation, like I said, they still want to make it better. And so you have other groups like, biochemists or biological engineers, trying to engineer these proteins, where it's like, hey, we can do better, or make them better adapted, or, more expansive optogenetics. And so just like this iterative process. So I think I covered everything that I wanted to cover about optogenetics, at least for the time being. So I'm pretty much almost certainly going to cover optogenetics again, at least in a couple weeks, because like I said, as mentioned by Neuralicia, we should be collaborating to talk more about optogenetics. They're probably going to do more of the talking, because they are definitely way more of an expert when it comes to like the strict optogenetics than I am, because they're a neuroscientist. But when it comes to maybe the genetics part, and maybe the protein part, that's a little bit more in my wheelhouse, and more of what I'm an expert. Which, that's more of the upstream knowledge, because like you don't really need to know the genetic modification stuff to understand optogenetics, nor do you really need to understand like the protein stuff to do or understand optogenetics. But I still think it's important to know. So I'm very much looking forward to that, and I'm very fortunate, and thankful that like I kind of like stumbled across a neuroscientist, or another content creator that also happens to be a neuroscientist. Pretty fortuitous. So I would want to wrap up with what I also did not get to cover yesterday, but I wanted to. With maybe a little bit more of a lighter topic, less technical. And I think is a good segue into Mental Health Awareness Month, which at least for me starts in about 22 minutes, May 1st. The month of May, I believe, is Mental Health Awareness Month. I should probably like fact check that. Yeah, month of May, mental health awareness. So with that, I mean, I've been covering psychological research. I think started streaming, but I think I'm gonna do a little bit more of an emphasis, at least for the month of May, and maybe who knows, going to the future, of like topics that hopefully maybe allow you to make improvements to your mental health, or address your mental health, or maybe empower you with knowledge to take steps to improve your mental health. but I don't want to make any promises. I just like covering this research because, like, I use this research in my own life. As I mentioned yesterday, I think I mentioned multiple times before, I attempt to practice mindfulness meditation. As I mentioned, I have an app on my phone that pretty much every morning, I just set aside 10 minutes and I follow the app through a guided mindfulness meditation practice. And the reason that I started doing that is because, like, I couldn't ignore the research. The research was like pretty robust and clear that mindfulness meditation has some benefits in terms of managing anxiety, coping with stress, I think potentially reducing your risk of experiencing depression, and maybe just allowing yourself to be in the present moment. So I use, so even though I'm not their biggest fan, I use the Waking Up app from Sam Harris, because, like, yeah, it does appear to be a pretty good app. And, like, their meditation practice is totally separate from, like, their opinions and their whatever political positions. But, like, that is the app I use, Waking Up. I think it's like, so this one. In addition, and they have since expanded, and the app appears to pretty much be in active development. Like before, I've had the app for going on, I think, 4 years now. Where before it was just like 10 minutes, and that's it. And that's what you're paying for. And I think it's like, I pay like $75 for a year subscription. So it's like, whatever, $6 a month. Not super expensive. But still not free. But I think, I could be mistaken, but I think if you just email them, or contact them saying, hey, I can't afford the subscription, I think they will give it to you for free. If I remember correctly. I could be mistaken. I'm pretty sure. But yeah, they have since expanded where, you have the option of 10-minute daily meditation. You can do 20 minutes, and there's a whole bunch of lessons as well, or other content from other, I guess you can call them spiritual gurus, so to speak, or at least what the app considers spiritual gurus, in terms of, like, if you want to maybe practice specifically, some self-compassion, or loving kindness, or maybe some lessons on some other topics, I guess, in the more mindfulness realm. Those are, well, you're getting a little bit of a preview here of, like, the illusory self. So overall, I think it's pretty good. Oh yes. So yeah, on the topic of mental health and why I started practicing mindfulness meditation, is because, like, the research was pretty clear to me. Like, hey, not much to lose, and pretty much high likelihood that you'll have some benefits if you start incorporating a simple mindfulness meditation practice in your daily life. And I'm not perfect, but I always try to, follow the evidence. And that holds true when it comes to pretty much anything, when it comes to my physical health or my mental health, even though those are one and the same. I exercise, and I'm heavily into fitness, because that's part of maintaining my physical health and mental health. And I take a science-based approach to that I think has been quite effective. I'm happy with the level of fitness that I have cultivated and maintained to this day. And I have done that through just, like, going into the evidence, curating it, and doing my best to follow it. It also is true with my diet. And it certainly haven't been perfect, but I've been satisfied with the result. And so I've pretty much just applied the same principles when it comes to, like, my psychological health or my mental health. Where it's like, yeah, I think the evidence is pretty clearly there that there are benefits to mindfulness meditation. So it's like, hey, I will start doing it. But there's still a caveat where, yeah, as I think I mentioned this yesterday. Pretty sure I mentioned this yesterday. Where it's like, yeah, the research is clear that for the vast majority of people, you are likely to get some benefits from incorporating a mindfulness meditation practice into your daily life. However, it does not appear to be universally beneficial, as in not for every single person out there. There does appear to be, and this is just what I have gathered from the research, but I could be mistaken, but from what I understand, there does appear to be a subset of people, a minority subset of people, that actually mindfulness meditation is actually, like, not good for them. If anything, kind of like contraindicated. Where, like, yeah, for the vast majority of people, mindfulness meditation will likely reduce their anxiety, or allow them to better able manage their anxiety. But there does appear to be a minority subset of people that actually mindfulness meditation can make their anxiety worse. Essentially a paradoxical effect. And so that's something to be aware of. Whereas as much as mindfulness meditation is like a good recommendation, and you should give it a shot, and most people will get a benefit from it, but you just need to be aware that it's possible that it can, it's a small chance, I can't emphasize it enough, that it appears to be a very small minority of people, but it does happen. They do appear to exist. That mindfulness meditation can actually make your anxiety worse, or like mindfulness meditation is like not good for you. That doesn't mean that you can't maybe try out other forms of meditation, even though mindfulness meditation gets the most coverage, probably the most research, and the more the most pop psychology coverage, so to speak, and the one that's popularized. There are numerous forms of meditation. I couldn't even list them all. Other ones that I know of are like transcendental meditation. That's the other kind of like semi-popular one. And so, like, maybe if you give it the old college try for mindfulness meditation and you really feel like it's not working for you, maybe something like transcendental meditation might be worth a try. So I just wanted to like get that out there. And let me just double check that. But like, I'm really confident. I don't know that I trust this people, even though generally speaking, good. I'm sure I have a paper. But I'm not going to do the research on. But I do remember coming across a couple of papers, sort of talking about the fact. A couple of actual research papers that allude to the fact that, hey, mindfulness meditation on the whole good, but not universally good. Let's see. A lot of the claims about meditation are for, yeah, totally. So it's not going to fix everything. It's probably not going to like turn your life around. Maybe small chance that it will. But like, yeah, I think generally speaking, it's not this like earth-shattering, mind-blowing experience. that's going to like solve all your problems for sure. It's just like you might just get some benefits. You might just maybe feel a little bit better on the whole as you go about your day. Excellent question, and that's actually an exceptionally good question. Because like when I first, started reading about it and, going into the literature, it's like, what are these concepts that they're talking about? Of like, what is mindfulness? Because like, I don't think that there's like a strict definition, as far as I can tell. There's kind of like definitions that researchers go by that are like, generally accepted. But like, what does it exactly, how do you measure it? Basically, here's where like, the hard scientist in me comes out. Of like, how do you measure mindfulness at an individual level? As far as I can tell, you can't put someone in a scanner. I could be wrong, but as far as I can tell you can't put someone in a scanner and like, oh, they're practicing mindfulness, and like, you can see it and observe it. And so it's kind of like, well, if you can't measure it, it's like, how do you know that you're doing it? That's kind of like the question that always comes to mind for me. But as far as I can tell, at least based off of the definitions that I come across in the research, mindfulness is just like being in the present moment, aware of kind of like being aware of your thoughts and feelings, but being aware of them in a non-judgmental manner. That's pretty much how I understand mindfulness. Kind of like the general accepted definition that I come across of like, you are in the present moment, but although that begs the question of like, what is it being in the present moment? I don't even know that I haven't answered that question. I know what it's like, or at least I have an idea of what it's like, not judge your thoughts and feelings. But I'm not sure I know exactly what it is in terms of like being in the present moment, and not judging your thoughts and feelings. But that is how I understand the concept of mindfulness. Don't get me started on grifters in LA. Yeah, so well, obviously you're my boots on the ground in LA, and I only know of LA of what I read. And even though the entire state of California, very left-leaning, there appears to be a lot of really pseudoscience practices out there, in terms of like whatever. I think astrology is pretty big in some like left-leaning crowds, and crystals, and whatever, Gwyneth Paltrow and Goop, and I think Gwyneth Paltrow is like very left-leaning and kind of like your stereotypical whatever LA person that is into these things, these things totally frustrate me. I figured for people, yeah, that's probably, so you're probably correct. Obviously I don't know for sure, but that would be my suspicion as well. And Romeo, welcome. Thank you so much for passing by. Hope you're doing well. You're gonna go crazy because you're tuning into this stream or for some other reason, but I hope you don't go crazy. And it's all, yeah, like it really blows my mind, the success of things like Goop, and like that straight science. Pretty frustrating actually, but whatever, I try not to lose. But yeah, all that to say, mental health important, and I make an attempt to take care of my, just as I make an attempt to take care of my physical health, as part of that, take care of my mental health. And that's why I cover research on mental health, because this is pretty much, we are on the RRL part of the R research. I don't know what to do. I'm not sure what RRL stands for. I apologize if you want to clarify. But like, yeah, I'm pretty much like going through the research that I use to hopefully like maintain my own mental health. Just as when I cover health research, like, you know, this study published pretty recently, a couple days ago, or no, accepted. When was it published? Doesn't matter. Oh, gotcha. Well then I empathize. And like, yeah, it's not the fun part of research. But like, yeah, you know, when I cover health research like this, in terms of dietary sugar consumption and health, I'm just going over like the research that I use to like hopefully guide my choices in my day-to-day life. Oh, Noda Bud, welcome. Thank you so much for passing by. Great to see you. And yeah, I know science. You don't need to tell me that science is fake. I just like spreading fake news. You know me, all too well. But yeah, I hope you're doing well. I'm hoping the warmer weather here, I'm hoping that holds true next door. So yeah. The importance of self-acceptance. Covered this a little bit yesterday. And I cover this for multiple reasons. One is that, well, it's like, yeah, it's the research that I use. And also, like, I very strongly want to push back on that notion. That appears to be in public opinion. That, oh, you know, like I mentioned yesterday, there's this sort of reaction towards, you know, body positivity, health at any size, or fat acceptance. And there's this reaction to it, this negative reaction to it, because like the sentiment is like, you know, we can't accept these things because like if we accept them, that means we'll normalize them, and there will not be motivation to change. Because people are under the false assumption that, you know, accepting something and changing for the better are mutually exclusive. And that does not appear to be borne out in the research. As in, like, you can be self-accepting of yourself and still be motivated to change. And like I mentioned yesterday, in the little bit of research that I covered, if anything, self-acceptance is actually might be a motivator or a core component in being motivated to change. It's kind of like, you know, once you are accepting of, let's say, your positive qualities and your negative qualities, and let's say you accept them and you're aware of them, you can still be very motivated, if not even more motivated, you know, address those things. Like I said, they're not mutually exclusive. So cool. Well, funny, well, not funny. Yes, I don't want to make light of your situation. But it's totally coincidental. Totally have research. You know, when it comes to maybe not the academic system, but kind of like the harsh environment in terms of Asian education. How, you know, it has maybe some negative effects, negative psychological effects. So if that's what you're experiencing, you know, my heart goes out to you, because that's not cool. So, there is this research here, and this is in the vein of what they call acceptance and commitment therapy, or ACT. You know, this is kind of like a specific intervention, literally aimed at designed at like, hey, it's in the terminology acceptance and commitment, where it's like it's kind of like part and parcel of like you can be accepting, and then from the place of acceptance, you are committed to change. Spoiler alert. So this is a meta-analysis, a systematic review, and meta-analysis. So it's trying to summarize the research for a body of research. Collecting together a bunch of papers and, filtering out the ones they want or don't want based off of whatever criteria that they use, and then trying to, synthesize some conclusions from it. And so as they conclude, ACT could be effective in improving weight loss, but more studies are needed to ascertain its effectiveness and the underlying mechanism by which the various components influence weight-related outcomes. Evidence obtained from a systematic review and meta-analysis of existing empirical studies. So, I think their language is appropriate. They're not making any sort of bold statements. They're pretty prudent, where it's this research appears to be in its infancy. And so it could be effective in improving weight loss. But, as usual, more research is needed, in that the quality of evidence doesn't appear to be overly high quality. And I think what's good about this study, if I remember correctly, is I think they grade the research. I could be mistaken. No, never mind. Think of another study. I might be thinking of this study. Oh yeah, I think it is this study. Yeah, it's this one, which I think is super great, where they go through the hierarchy of evidence. Many people will just get any study to back up whatever claim that they want to make. Maybe not recognizing that, whatever paper that they've quickly Googled is the lowest, on the lowest rung on the hierarchy of evidence. Of hey, you've used some really bad quality evidence to back up your claim. Because not all evidence is created equal. And there's totally kind of like a hierarchy or a pyramid of evidence that I think more people need to be aware of. If only they were that easy. But meditation might be a component of a weight loss strategy. There is such a thing as mindful eating, or being mindful of what you eat, or as you eat. And if I remember correctly, when it comes to the research, those who practice mindfulness as they're eating, or who eat in a mindful way, whatever that means, I think they tend to eat less. And yeah, you're definitely not wrong there. That encapsulates pretty much, like you said, every study ever. Hey, we did good, but more research is needed. So, according to the World Health Organization, the global prevalence of overweight and obesity is estimated to be more than 1.9 billion and 650 million, respectively, with that of obesity nearly tripled between 1975 and 2016. This has been attributed to the global trend of increasingly unhealthy eating habits, particularly in the consumption of energy-dense, high-fat, and sugary food, and sedentary lifestyles, leading to chronic health consequences such as cardiovascular diseases and type 2 diabetes mellitus. To improve dietary and physical activity habits, numerous interventions have been implemented by multiple stakeholders at the global, regional, and local levels. These include population-wide surveillance systems, education strategies, and individual lifestyle adaptations. For example, using standing desks during work. However, dietary modifications are challenging for many people with overweight and obesity, as it requires a large amount of self-regulation to restrict their calorie intake. This is worsened by common maladaptive eating behaviors, such as emotional eating, which I think more people need to be aware of. I think, many people, uh, many people understandably use food as a coping mechanism. I'm certainly guilty of that from time to time, for sure, 100%. But I think many people overlook or simply not aware of the emotional component of eating or food choices. External eating and restraint eating, which respectively refer to disordered eating in response to emotions, for example, stress and sadness, external stimuli, for example, visual and smell, and the cycle of food intake restriction and indulgence, which I think this alludes to kind of like binge eating. Acceptance and commitment therapy is a third wave cognitive behavior therapy that has been shown to improve both mental and physical conditions, including anxiety, depression, stress, and chronic pain. At the core of acceptance and commitment therapy is the strategy to cope with averse internal thoughts, feelings, and bodily sensations by exercising mindfulness and psychological flexibility. Which I probably want to do an entire stream devoted to psychological flexibility. Uh, quite a bit of research when it comes to that. And psychological flexibility appears to be pretty core component or fundamental component of maintaining kind of like good psychological health or resilience, so to speak. And that seems to part of that seems driven by the fact that a lot of, let's say, mental health issues or mental health struggles kind of like can be framed as like stemming from not knowing when a strategy is no longer useful or to abandon a strategy, which is like easier said than done. Take things like whatever. Pick your mental health issue, anxiety, depression, PTSD, or complex PTSD, or attachment insecurity or attachment issues. Like a lot of these things in a certain context, like they are adaptive. Like these, I think, in my opinion, based off of what I know and my understanding, like these things occur, often as the result of something or some sort of external event or the conditions in which you're in or your environment. And they can potentially allow you to adapt to a certain environment. But at some point, they become maladaptive, or it's like if your environment changes, this strategy no longer is useful or adaptive. And so it requires psychological flexibility, maybe recognize at the very least that, hey, at one point, maybe this anxiety or depression was actually adaptive, actually a good thing, allowing you to survive or get through the day. But maybe now it is no longer useful. Or even something is not simple, but whatever, viewed as benign, of like emotional suppression. It's like there's totally a time and place suppressing your emotions. You don't need to be always like emotionally expressive or aware 24/7. Kind of spoke about this yesterday with the Discord conversation. Like there's a time and place of like setting aside your emotions and maybe ignoring them for the time being. But doing that over the long term, or if you're not returning to process those emotions, they're probably going to somewhere down the road become maladaptive. Want to kind of bite you in the ass at some point. And I think that's where the psychological flexibility comes into play. Of like a kind of like changing your strategy. Strategy, yeah, let's see, where was I? Yeah. So cognitive diffusion, being present, self as context, values, and committed action. In the context of weight management, acceptance and commitment therapy could improve one's ability to cope with the negative psychobehavioral effects of food cravings, by taking these psychological experiences into perspective and committing to healthy behaviors that are coherent with the individual's value-based goals. This was hypothesized to improve weight management by improving the acknowledgement, acceptance, and self-regulation of overeating impulses. This also prevents one from feeling negative due to a dietary lapse event, or that is unintended eating, which could trigger an overeating episode. Right, and I think they're touching upon, in my opinion, pretty important concept of like, in my opinion, and also in my experience, like working towards any goal. And I think, this is just like summarized in like the saying, like progress is never linear. Like when it comes to weight management or weight loss, like there will always be setbacks, or as they call a dietary lapse. And it's just a key component of, let's say, achieving your goals or managing your weight, is recognizing that, a lapse will happen, and how do you deal with that lapse? As in, if you deal with it, let's say, in the less than optimal way, they say it could trigger an overeating episode. It might be kind of like self-sabotaging. If you don't happen to deal with the lapse appropriately, or in a less than optimal way. And I think that also holds true, at least I'm definitely not an addiction expert, or an expert in recovery, but this is just from my understanding when it comes to just like addiction recovery, or recovering from substance use disorder. It's like, relapses are pretty common. I think it's pretty rare, as far as I can tell, it's pretty rare, where, someone just, whatever, goes to recovery or rehab, and then like, oh yeah, they're done with the substance, or like, like overnight, they are now perfectly managing their substance use disorder. Again, as far as I can tell, some sort of relapse is like bound to happen, no matter like how do you deal with that relapse. Does it result in like further spiraling, or do you have the appropriate tools and strategies of like recognizing when you lapse and how to deal with it, maybe in a more optimal or healthy way? That's kind of like the more extreme. But addiction and substance use disorder, super complicated, complex topics. But that is just sort of some of what I know, or some of my understanding when it comes to recovery. Several systematic reviews have examined the effectiveness of acceptance and commitment therapy for weight-related behaviors. In 2020, a systematic review and network meta-analysis with adults who were overweight or obese showed that acceptance and commitment therapy has the most consistent effects on improving weight loss beyond 18 months, as compared to mindfulness-based cognitive behavioral therapy, compassion-focused therapy, and dialectical behavior therapy. Interesting. Pretty bold. And that's also, kind of like on the topic of, let's say, a lapse or relapse. And I also would draw upon some of my experience as a personal trainer, of like, one of the traps that people fall into, where many people can lose weight. And actually, many people can lose like significant amount of weight. But when you track them over time, it's that effect of like, yeah, they can lose weight, but very quickly, they put it back on, and very frequently, they put on even more weight than previously. It's really like, over the long term, does the change happen? Where it's like, that's pretty much, that is in the category of like kind of like a relapse. So like, yeah, they can like commit to a weight loss program, lose weight, and they can keep it off for a certain amount of time and kind of like achieve their goal of like a desired weight. But then the question becomes like, can they maintain the weight loss? And very often, unfortunately, all too frequently, It's like, yeah, they can't maintain the weight loss. And very often, they'll regain a lot of the weight and then some. However, the effects of acceptance and commitment therapy on the various outcomes were unclear. Another meta-analysis on a general adult population showed that acceptance and commitment therapy improved physical activity in the general population, but little is known about its effects on people with overweight and obesity. Moreover, the variability in the types of physical activity examined across the studies may have impeded the comparability of the findings. Another systematic review with adults who were overweight or obese showed mixed feelings on the effectiveness of acceptance and commitment therapy on psychological well-being. For example, quality of life, depression, stigma, eating behaviors, and weight loss. This could be due to the inclusion of articles that compared the effectiveness of acceptance and commitment therapy with control group conditions that receive standard behavioral therapy and no intervention. Where the mean differences between ACT and no intervention are likely larger and hence statistically significant as compared to standard behavioral therapy. To the author's best knowledge, there has been no meta-analysis on the effectiveness of acceptance and commitment therapy-based interventions on weight, eating behaviors, and the quality of life of those with overweight and obesity. Hence, the current study addresses this knowledge gap and provides an important review of this growing body of literature. But this is a systematic review and meta-analysis. They allude to some of the past research in the introduction, showing how at least some preliminary evidence demonstrating that acceptance and commitment therapy appears to have some advantages over some other interventions like mindfulness-based cognitive behavioral therapy, compassion-focused therapy, and I've totally covered some research on self-compassion, and dialectical behavioral therapy, which I would say is pretty popular intervention, if not one of the more well-known ones. More well-known and researched, I think. They search the databases. They try to gather a bunch of papers and put them all together. This is like the typical flow chart or figure of their screening process of all the databases, Cochrane Library, Web of Science, blah, blah, blah. So they remove duplicate records, they exclude some, but pretty much in the end, they go through a lot of exclusion. So non-randomized controlled trials, only abstracts, etc., etc. So they total records included in meta-analysis, total records included in review, so basically 14. And they started with, I think, thousands. Database records identified from, so it's approximately 1,400. And they narrowed it down. So, literally, that's 1%. They literally excluded. If I have my basic math correct, and I think I do. That is not the number. Yeah, that is 1%. So they're literally excluding 99% of the research that they got from the databases. So, arguably, 99% did not meet the inclusion criteria, and or were basically, not the greatest quality. So overall, what do they find? To our best knowledge, this is the first systematic review that examined the effectiveness of acceptance and commitment therapy on weight, eating behaviors, and psychological outcomes by pooling effect estimates through meta-analyses. Overall, our findings suggest that acceptance and commitment therapy is effective in improving certain antecedents of weight loss, such as psychological flexibility and weight-related stigma, which could eventually translate into better behavioral and emotional self-regulation of eating habits. However, its effect on actual eating behaviors and weight loss could be influenced by other factors, including time, dietary intake, physical activity, dietary habits, and socio-environmental circumstances that were rarely explored in the included studies. Sorry. We found that acceptance and commitment therapy-based interventions were effective in improving weight loss in terms of BMI, but not that of body mass. So talking about BMI, there's a lot of controversy, and let's say there's a lot of understandably negative reaction towards BMI, because many people understand, you know, a lot of potential flaws associated with BMI. Definitely a far from perfect metric when it comes to whatever measuring body weight or determining a healthy body weight, but still has some utility. Still kind of like the best, as far as I know, the best tool that we have. So quickly classifying body weight as whatever in the ballpark of healthy or at risk. There's definitely kind of like a giant asterisk when it comes to BMI. It is not totally useless. It's not, in my opinion, not totally useless. And this is coming from someone who is technically classified as overweight according to BMI, but I'm highly confident that I have a very low body fat percent. It's just the fact that, I have a decent amount of muscle mass classifies me as technically overweight. I think I'm like either pretty much like right at the cutoff or right below the cutoff of like normal weight and overweight, or like right above the cutoff for overweight. I think technically to be overweight, you need like a 25 BMI. I think literally my 24.9, like 25.1. Yeah, all that to say, very serious flaws with BMI, but not useless. The significant finding on BMI could be due to the over-reliance on the results from one study, which was analyzed with a weight of 97.3%. So yeah, they might be overly considering one particular study. Therefore, we are inclined to infer that ACT, acceptance and commitment therapy, has a minimal effect on body weight, especially when compared with standard behavior treatments. This coincides with another meta-analysis that reported a non-significant effect of motivational interviewing plus cognitive behavior therapy interventions on weight loss, suggesting the need to consider other factors that influence weight loss, such as diet and exercise. The non-significant finding could also be due to the different underlying mechanisms of how ACT influences behavior. For example, while the concept of acceptance in ACT promotes the acceptance of negative internal experiences, such as anxiety, the need for acceptance in the case of weight loss is in accepting the impending reduction in pleasure from diet and exercise modifications. Future studies could consider examining this speculation and tailoring the ACT-based weight loss. Interesting. Only 3 included studies reported the delivery of ACT by personnel trained in ACT or acceptance-based therapy. Yeah, that's pretty important. Where it's so like, these are interventions or like modalities that understandably required qualified personnel like administer and get the information across, like the patient, I guess in this case. And so like, yeah, ideally you need like a qualified trained professional, which there's almost, just as there are good doctors and bad doctors, and I've definitely encountered both. Thankfully, more good than bad. But like, yeah, that is likely true when it comes to personnel, ACT. Although the students and non-specialists had received formal training for the research, they were neither professional therapists nor did they have practical ACT background apart from during their training. Although a study showed that ACT could be effectively delivered by people not trained in ACT, there was limited report on the direct comparability, the treatment fidelity, between those with and without ACT training. On the other hand, the interventionists mentioned in the included studies could have undergone ACT training but was not reported. Future studies could consider training the interventionists in the concepts behind ACT and reporting their training status. Acceptance and mindfulness-based psychotherapies are theoretically grounded in East Asian philosophies. However, all studies we reviewed were either from USA or Europe, UK, Portugal, and Finland. Unfortunately, this is also reflective of the knowledge gap in eating behavior-related research, where understanding across the diverse cultures and contexts globally is currently lacking. Nonetheless, there is a growing body of research on the use of ACT in non-Western cultures, such as Sub-Saharan Africa and China, though their effectiveness for intervening eating behaviors and weight management remains investigated. So it's, that's, I think that's an important thing to at least consider, or whatever, be mindful of, or at least it's interesting, that as they say, grounded in East Asian philosophies, this acceptance and mindfulness-based psychotherapies. And yet, even though I think this is changing recently, at least when it comes to, as far as I know, in terms of China and India, it's like, generally speaking, so you're almost certainly way more well qualified to talk about these things than I am. Boy meets Mini. But, I understand, at least based off of some of the things that I read, of like, there appears to be a little bit of a rise when it comes to overweight and obesity in China and India. But I think generally speaking, on the whole, the East Asian countries, have, let's say, lower body weights. They're essentially, in comparison to the United States or Canada or the UK, they have much lower rates of overweight and obesity. And yet, interestingly enough, like, we're using like an East Asian philosophy to potentially address overweight and obesity. But like, is it the East Asian philosophy that is resulting in the lower rates of overweight and obesity in these East Asian countries? I don't have an answer to that question. But it's like, where you're basically, using something from an entirely different cultural context and trying to adapt it to essentially like a Western cultural context. So like and these are obviously certainly not perfectly adapted, right? It's just like extracting something from the philosophy and kind of like westernizing it, arguably diluting it, and seeing if it helps whatever Western individuals or westernized individuals. To do India, that makes sense. Higher caste people have more. Yeah. Though, 1,000. Definitely no argument from me there at all, based off of everything that I know of the caste system and what I read. Seems like to be a pretty abhorrent. And I definitely I have some close friends. I have one close friend, particularly close friend, like specifically from India. And like, who immigrated from India to Canada. They are definitely grateful in Canada. They definitely have a lot of negative things to say of India, and they have like absolutely, as far as I could tell, zero desire to even like visit back home. Overall, our findings suggest modest effects of acceptance and commitment therapy on weight loss, but more rigorous randomized controlled trials with larger sample sizes and more precise effect estimates are needed for more balanced meta-analyses. Having more relevant studies available would also provide adequate statistical power for subgroup analyses to estimate the effects of control group condition differences in moderating the meta-analysis results. Future studies could consider integrating concepts from ACT and behavior change techniques that have been shown to improve weight loss to enhance the effects of current weight loss programs. Longer follow-up outcome evaluations may also produce useful information on the effects of ACT on weight loss and eating behavior. There are several limitations to this study. First, we only searched English databases and could have missed out on relevant articles found in databases of other languages. Second, the reported studies had limited mention of the treatment fidelity and adherence to certain checklists for a direct comparison of intervention components and whether they can be classified as an ACT-based intervention. Despite the heterogeneity and potential issues in comparing the interventions, we focused on identifying and comparing the studies where meaningful comparisons could be made. In addition, we identified a small subset of suitable studies for a meta-analysis of the effective change in weight, eating behaviors, and psychological outcomes, quality of life, depression, psychological flexibility, and stigma. I think that basically wraps up meta-analysis. Oh yeah, they also go through, I think nicely, these brief bullet points. So what is already known on this subject about acceptance and commitment therapy? ACT is effective in improving symptoms of mental health conditions such as depression and anxiety. ACT could improve weight-related outcomes such as weight, body image, weight stigma, and eating behavior. That's what's kind of like the current state of knowledge. And so what does this study add? So that ACT is effective in improving psychological flexibility and weight stigma in people with overweight and obesity. Mixed findings were found for the effectiveness of ACT on weight. Limited evidence supports the effectiveness of ACT on eating behavior, quality of life, depression. So like, yeah, basically, even though there's, let's say, a glimmer or a hint of like positive outcomes when it comes to acceptance and commitment therapy, when it comes to weight management, more research needs to be done. And this is a recent study. This is a recent meta-analysis and systematic review published in 2023, so like this year. I think this is basically about as up-to-date as you can get. There's been something published, I don't know, last week. This is essentially emerging research. But, it seems like on the whole, acceptance and commitment therapy overall has positive outcomes. And at least based off of this, no real drawbacks per se, other than, it's still a little bit of an open question on whether acceptance and commitment therapy is actually, effective for managing your weight or, weight reduction. So, kind of like to be determined, or still a little bit of an open question. But there is still, a little bit of other research go by. But this is a little bit older, so 2017. But there's, randomized controlled trials. This is the title of the paper, exploring the efficacy of an acceptance, mindfulness, and compassionate-based group intervention for women struggling with their weight. So, this is a specific demographic, so maybe it might be exclusive or only limited to women. So something to keep in mind. But still, all this to say, it's like, I'm not trying to market acceptance and commitment therapy as like the best weight management or weight loss strategy. I'm more or less just trying to get the message across that it's associated with like overall positive outcome. And at the very least, okay, it's not like, it does not appear to be, I think it's pretty clear, it's not resulting in like weight gain or like negative outcomes. It's basically, neutral, at least as far as I can tell, neutral to positive. Of like, hey, it might not be resulting in like dramatic weight loss, but, doesn't appear to be resulting in like, people becoming more and more overweight or struggling with their weight over time. And that's really ultimately the notion that I want to push back against, because like people have this opinion, like I said, that we can't accept body positivity or health at any size. Because like if we accept these things and people don't want to change these things, that does not appear to be true. Our findings suggest that the use of ACT for weight loss and eating behavior improvements is at an early stage. Yeah, in its infancy. or like emerging evidence. The effectiveness of ACT in this application was found to be of limited effectiveness in changing weight-related outcomes and eating behaviors. The observation of wide heterogeneity in how ACT-based interventions are currently conducted indicates that future research should aim to create a standard procedure or guidance for interventions to improve their reliability and validity and to allow studies to be replicated. Finally, future research should also investigate the use of ACT in non-Western cultural contexts to address key knowledge gaps in both the ACT and general literature in weight and eating behavior research. Also Poser, welcome. Much for passing by. Hope you're doing well. Any attempt to solve a problem consume someone's thought towards the problem. Ineffective strategies are categorically bad. Yeah, you're not wrong. Say where it's like, yeah. I think I take your point that you're trying to make. Of like, hey, if this strategy is not getting you towards your goal, it's a wasted effort. I don't know that I would use the term bad. I would just maybe say suboptimal. Or like undesirable. But I totally take your point. But I mean, at the end of the day, as far as I can tell from the research, there appears to be no universal recommendation of like, hey, this is the best psychological intervention that results in, significant weight loss or weight management. At least that's my understanding. I could be totally wrong. But I think, research like this exists for a reason. Like, we are still trying to determine, like, what is the optimal psychological intervention that results in, the greatest weight loss or the most effective weight management, etc., etc. Or maybe even just like trying to answer the question of like, there's probably not a one size fits all, right? Maybe just trying to figure out like, oh, this psychological intervention or this modality effective for this group of people, or sample or cohort of individuals, and this other modality or psychological intervention good for these types of people. I don't think we're necessarily searching for like, the panacea that will address all of everyone's weight issues. They have them. So yeah, I was gonna go over this research, but I think going over the meta-analysis gives a good summary. Pretty much the most up to date. And also, probably gonna take me a while. I think this one's a little bit longer. Yeah, that too. I'm definitely not about solving problems. But like, I do think, even even if it's like not optimal, just even showing something that is potentially beneficial, still has value and utility. I think, my opinion. But I think we're gonna leave it there for tonight, because I think this is like one of the few streams that I basically covered all I wanted to cover. I got through the optogenetics stuff that I wanted to cover, which I'm happy about. Whether I actually covered it in a good or meaningful way, can't really say, but I did try. And I hope I at least covered the fundamentals. Yeah, basically the main messages that I want to get across when it comes to optogenetics is that, it's a powerful technique. A powerful technique that has a lot of potential, can answer a lot of questions, and can be potentially used in various fields and domains, not just neuroscience. And pretty much, the ultimate message, the ultimate sort of like broad overarching message is like, I think it's a good example of, like I said, multiple fields coming together that results in this powerful technique. of, like I said, innovations or discoveries in microbiology, finding these cool proteins in, green algae or other microorganisms. And through genetic manipulation, we're using them, these light sensitive proteins discovered in microorganisms in, mice, and other non-human animals, and fruit flies. And we're trying to ask questions, uh, trying to answer questions about neuroscience and the brain. And we are able to, get these light sensitive proteins um, into, these non-human animals through innovations in, genetic manipulation and engineering. And even then, we're not done attempting to innovate. That's why I cover this paper from, let's say, the biochemistry perspective of, like, now we're trying to, like, one strategy to make the technique better is, hey, maybe we can make the proteins even better. Taking what we find in nature, and hey, maybe we can make improvements on nature, at least for our purposes. And that holds true as recently as, like, 2019. Of, like I said, as powerful as this technique is, there are still potential challenges that they want to overcome to make it better. And so they're still trying to carry out protein engineering on these channel rhodopsin to address some of these challenges and hurdles, takes the technique even more forward. So that's pretty much the overall main message, broad message that I want to get across. So with that, let's find someone to raid into. I think... Ooh. Katie is streaming. Fellow... Let's see. Not a science streamer. Kind of a political streamer. But still a radical lefty streamer like myself. So I think we're gonna raid into that up. But yeah, I want to thank everyone that passed by. Boy Meets Mini, always a pleasure. Great to see you. Thank you for passing by. Thank you for the great questions that you asked. Yeah, you asked some really fantastic questions, which I super appreciate. And thank you, Bob Marley. Thank you, All Supposer, Desolate Mirror, and then anybody else that I forgot. Romeo, thank you for passing by. Much appreciated. And yeah, my heart goes out to you. And let's say your experiences in the Asian education system. Thank you, Neuralicia. Shout out to Neuralicia. Do that again. One moment. Where it's like, yeah, we plan to collab in a couple weeks. I think almost in exactly 3 weeks. I think the date that we set is May 21st. And I think we're going to be returning to optogenetics. And maybe, my hope, it's up to them, but my hope is, we can cover other research more down the line. And always great, again, to run into another scientist that's, passionate about science communication, and that, hopefully I can actually consult with an actual expert in neuroscience and psychology when I talk about neuroscience psychology. And I think so far, I don't think I made any grave mistakes so far, but I'm sure it's somewhere down the road I'm gonna make some grave error. And I'm super glad to hear that you learned something new. That is pretty much my ultimate goal. So I plan to stream next Since unfortunately the workout streams are on hiatus for now, I should be streaming, I think Tuesday or Wednesday, to be determined. That's my goal. I will be letting the Discord know when I'll be streaming next. Join the Discord. Feel free. That should be a link. Yes, there we go. So like, yeah, thank you everyone. Super appreciated. We're gonna raid into Katie. If you're not following Katie, you should be. They're a radical lefty like me. They have great conversations. They go on panels, and they do a whole bunch of other entertaining stuff. So yeah, that's gonna be it for me. We'll be back Tuesday or Wednesday. Gonna let the Discord know. And until next time, take care, well, kind, and yeah, can't thank everyone enough.
Sad anymore. I'm not sad anymore, no more now. I'm just mad at myself for being dumb.